do you have on the Monday or the Tuesday papers or anything? Okay.
Do you want us to send an email every day?
No. Didn't you get the second one already?
I went to sleep before you sent it.
It's in your mailbox.
Okay, thank you.
We got some new people in the class. Are you MIT people?
Yeah, absolutely.
Absolutely. Well, here's the form. If you want to get the papers handed out, just send me an email with that address, and we'll give you the email. And okay. Wait another couple of seconds.
Wait for the network.
Today we're going to continue beyond where we were yesterday and the day before. So we've covered the survey, electrochemistry, materials, controls. Yesterday I introduced a survey of aqueous cold fusion systems, and I introduced the flux equations, which I think is the engineering way to control these devices in aqueous systems. So a little different in dry systems, which is what we're going to talk about today. So let me just do a quick survey. The reason we like cold fusion is that the fuel deuterium is abundant. It's up in the clouds up above. I showed you that in the coffee, the deuterium, the deuterons are at approximately 900 micromoles, and you can get enough energy out to keep a small plane in the air for about 2 hours with your cup of coffee's deuterium. It's safe, it doesn't make CO2, and is perfect to fight the greenhouse effect and the pollution, which is the bigger problem from oil. And it has an incredibly high energy density. If we plot out the energy density in this direction, we plot out the power density in this direction, and compare cold fusion to fuel cells and batteries and lithium batteries and supercapacitors, we're way beyond. We have higher power density, higher energy density. And as we talked about on the first day, the reason we do this is within palladium, unusual conditions occur. And unlike all other materials, we get an incredibly large hydrogen capacity. And if we do not have defects, if we do not destroy the lattice, we'll be able to get cold fusion. When we apply an electric field, we have both polarization, where we have charges that separate, where we have dipoles that rotate within the electric field, and we have dissipation as well. And the most important thing I pointed out on day one was that water is more than just a dipolar rotation and cation and anion drift. In fact, there are defects that occur from the deuterons or protons, if it's ordinary water, where we end up getting drift of these to the cathode through these drift ellipsoids. And what happens here is the Vollmer reaction. And if the Tafel reaction, as Peter pointed out, occurs, the deuterium or the hydrogen leaves as a gas. And we talked about temperature, we talked about specific heat and how we measure, and the temperature is not the way to calculate the amount of heat, because we also need the mass of the material as well as its specific heat. And we couple that with measuring thermal conductivity. And so we end up being able to measure if we have excess heat by looking to see the following parameters. And we're going to see a lot of these today when we look at nanomaterials. One of them is at rise in temperature, and we like to divide it by the input power. The heat flow, we like to divide that by the input power. We'll show you why. And we do time integrated, ohmic control, calibrated calorimetry. We talked about those other things. And basically the way we do it, although this is not the geometry we use a good geometry. In this cartoon-like representation, we have our cold fusion device. We put it right next to the ohmic control. We put at least 1 or 2 sensors in between the two, as well as decorate the entire system with a series of sensors. And we also measure the heat flow out. And in the wet systems, we use serial integration. We haven't done that yet with the dry systems. And we talked about that you want to measure your calorimeter when you do your measurements and calibrate it, that when you put in a square wave, you get out a square wave. You want to always do a noise measurement so you rule out those false positives. And basically, at the end of the day, we showed clear, reproducible demonstration for the first 2 days of excess heat. So we're up on second base, and I showed you that we've made some efforts at trying to get to third base with making electricity. And the reason that's interesting is we got to power gains with aqueous systems, 5, 7, occasionally 30, 40, and that was it. And it was very hard to do the feedback loop. We showed you that when we actually tried to make electricity, we were losing 55, 60% of the energy to the fuel cell, 5% to the leads. We were discovering where we were going to get losses, where our fusion community ought to be, but there aren't. Anyway, I showed you thermal spectroscopy, where we're looking at power on the left, we're looking at energy on the right. So here's our power curves. We're going to see these over and over with the dry systems as well as the aqueous systems. And we always have a control and compare it to the device. And we talked about that there's a superlinear rise on the energy. I pointed out to you that this is the energy gain. We pointed out that there are noise levels involved, and with the ohmic control, we'd like to get a match. And that was with the nickel systems. And then we showed several palladium heavy water systems here with platinum as the anode, where here we put the input to the control, we get the output that matches, and we get more out from the cold fusion device for different inputs than we do to the ohmic control. Then we talked about flux. We showed that the TAFA loss, this is the entry. This was, we talked about with metamaterial, that there's a flow within the metal. I pointed out to you that if you look at the flow equations, we can divide by concentration. We get the first order rate equations, and that's really interesting because it tells us what goes in is what gets ordered by the electric field times the electrophoretic mobility minus what goes up in the gas, and this is on the order of 0 what you lose from fusion. And then we talked about that if you apply the Einstein relation, you end up getting this, where we see that the amount that enters is a ratio of 2 energies, the ordering energy, the applied field, over the disorder of KT, and minus what you lose as a gas. And the result of that is that we now can do co-deposition, where we look at both deuterons and palladium, have them come down at the same time, and compared to normal cold fusion, which is here, we get a very, very fast loading ratio. And we pointed out that there's a slight difference between what we use and what Spaywars uses, where they deposit onto copper, silver, and other metals, and we deposit onto palladium. And we talked about optimal operating points, the fact that when you look at cold fusion system, every cold fusion system we've ever looked at, whether it's for the production of tritium or helium or excess heat, no matter what we've looked at, we always find that there's a peak. And what we see is over here, we have limited loading. Over here, we're getting too much TAFL, and we're losing it as DO2, plus there's other reasons. I think that over here on the right, we are also losing phonons. And what happens is, well, we'll talk about that later. Let's go to here. We talked about that when we looked at a number of configurations, the fusor was way up compared to all the others. And we talked about the fact that when we optimally operate these, we get just large single bubbles. And the fact that unlike Fleischmann and Pons, where the electric fields all come together into an equilibrium-like configuration, we get something where at equilibrium, we're getting flow through the metal. And the result is with the fusors, this is a result from a dual calorimetry system where we have a cold fusion device here, an ohmic control here. We'll have the electric current go through both an electrical series. We'll measure the voltage over the ohmic control, the voltage over the cold fusion device, and measure the temperatures. And that allows us now here to look at input power. So here are the curves that go to input power. These curves are energy, they go to the right, and we're looking as a function of time. And what we can see is in the ohmic control, here we're getting out in the blue, there's a little time lag. We're getting out what we put in. And when we look at energy, there's a nice match. That is break even. We do not get excess heat there. On the other hand, when we put in energy into the fusor here in light purple, in the red, we look at the power out. We are getting more out than we're putting in. These curves separate, unlike here where they're parallel. So here is our excess energy. Here is our power gain. And it turns out here there was some heat after death, which, as we pointed out, Fleischmann and Pons noted when one of their cells dried out, they kept getting the heat and gave it that horrible name, heat after death. And what it is power that comes out after you apply the electric field intensity. And when you do the time integral of that, that is what they call heat after death. Finally, what we showed yesterday was that if we take the heat after death, here's another system. The blue and the green are matching here in energy. These are the ohmic controls. Here is the fusor. Here is the output of the fusor. So we're getting power gains. This is on a log curve, so it's tougher to see, between the yellow and the red. And here's our energy. And we can see at the end there's heat after death. And we showed you that we could take the heat after death and yet another experiment and heat up a second bucket using a thermoelectric device. So we were able to do work from heat after death. Finally, we talked about the fact that when these devices are putting out excess power, what we see is that in the near infrared, we can get an image, here it's off, here it's on, and we don't see it for the ohmic control, even when it's a higher temperature, such as here. So here you see that here's the input to the fusor, here's the temperature, which was less than the temperature of the ohmic control. When we look at the output over the fusor, we're getting increasing output only when it's giving out excess heat, and we didn't see it at a higher temperature there. Finally, I showed you we can do these aqueous cold fusion systems to propel with Stirling engines motion. So here, for example, is a Stirling engine above a cold fusion reactor, and here's another one above the ohmic control. And we make it like this so we could switch back and forth, and we got an average gain of 170%. And finally, I showed you that when you run this and look at the calorimetry at the core, we lose the excess heat at the core because we're taking the energy out. And you can see here it's over unity, and we lose the over unity. Finally, we talked about for making electricity, we've been looking at trying to get the feedback loop. And our big problem is loss from wasted heat in wires and switches, not much wasted heat in the first stage. But to run the fusor, we're running it between 600 volts and 1,000 volts or 2,000 volts. So we have very poor efficiencies when we go to the higher stages. And the reason we think we're going to make it with the NanoRs, as you'll see, is they're driven at a lower voltage. So we may be able to then come around for the feedback. Anyway, that is what we're shooting for. And today we're going to talk about dry materials and how we incorporate them and measure the excess heat from these materials that are incorporated into two-terminal devices that look like resistors. Questions? Okay, dry materials. A lot of people have taken part in these investigations, and what we mean by a NanoR is this two-terminal device filled with a active nanomaterial that has cold fusion properties. It has either palladium or nickel as the active material that interacts with one of the isotopes of hydrogen. And what we do is we put an electric field through it, and we find that that stimulates under certain conditions, getting excess energy out. We always use an ohmic control because without that, we can't really calibrate it. And we can't convert the thermometry to calorimetry. We set up a company called NanoTech to make these devices. And each year we've been increasing the output by at least a factor of 10 is what it looks like. Okay, nanomaterials. We are making the nanomaterials when we make co-deposition. It is highly likely, as Peter will describe today and tomorrow, that it may be that the key to the very robust properties of the nanomaterials compared to the aqueous systems is it could be their ability to lose the product and make that site open. But we make these with CoDep. We believe that Arada made them with platinum black. We have a number of people who've worked with the zirconium oxide materials that we'll talk about. And we use some other types of materials we're not talking about yet. It turns out that there is a plethora of materials you can use. You can make complexes in aqueous systems. You can make nanostructures directly from palladium wires. You can make the nanoparticles on a carbon surface. There's a whole series of ways to do it here. This one's really interesting. If you have time to go into it, I'll send you the papers again. If you send the email to the address, as I've sent you the papers the first 2 nights, we'll do this for the next 2, and then you can investigate these other materials. So here's what they look like, some of them. These mainly, most of them are zirconium oxide with palladium, and what we add is deuterium or protium, and we end up getting materials that are nanostructured that have this range of content by weight. Zirconium ranges around 65%. The palladium can vary anywhere between 4 and 30%. And we've investigated over the last 4 years other metals. Now, what we think is occurring when we make these materials is that we end up with something that looks a little bit like a chocolate chip cookie, if you want to think about it, where the chips are binary metals like palladium deuteride, and around it is a highly insulating material, zirconia oxide. And so the metals act as islands, and they can't quite get electrically to the next island. And that's why we see that these devices and materials have extremely high electrical resistances. Questions? Okay. Another thing we found when we began using these is the nanomaterials have very high loadings. Ab initio, you put up gases, you can get what appears to be loadings of 3, but are they? What probably happens is many of the nanomaterials have voids in the center. They probably have shallow traps. I don't think these numbers reflect the actual loading at the active sites. I mean, the active sites may be 1, and these other shallow sites are what gives us these higher numbers. Questions? Okay, here's a SEM of the materials, and then an analysis of the elements within it. Here's, this one had nickel, here's zirconium, oxygen, palladium. Now we've tried to understand better about size and its relation. There was a discussion before we started today about the fact that, is it true that cold fusion materials are most active when their size is 7 to 20 nanometers or the like? And that's a really good question, and we need that data. We use a multi-step process to make them. Most of them are proprietary. We don't talk about them. The sensor referred back to. Although the patent office, to every patent application I put in, has been disrespectful in not even reading what was submitted or the response that was submitted, and say always that cold fusion doesn't exist. This particular patent we filed, and within 2 weeks we were told that they wanted to decide if they'd make it secret. So that's what all this refers to. Anyway, here's what the Series 1 nanors look like. We like to put in here, we're using copper. We've got the nanomaterial here. We see that the specific gravity was about 3.7. The electrical resistivity, that should be megohm centimeters, range from about 3.5 to 4.6 megohm centimeters. Later on, we went through a series where we tried to put the probes in the center. It wasn't really needed. We made more complicated ones. And here were the last batch that we made since the last course, where I'll show you some of the results we made and discoveries we made over the last year using these Series 7 devices. And here, for example, we see one of these Series 7 nanors, and the ohmic control is packaged right in it. And what we like to do is take a magic marker and show where it is before we wrap everything up in the thermal material. What I won't talk about today is we've made transistors out of the nanomaterials. We've made other devices with the nanomaterials. We've made ultrasonic measurements, and that's a little bit beyond here. In the case of the transistor, you have to have two controls, and we showed that there was excess heat coming out. We showed that there were two optimal operating points for both of the voltages, and we showed that there was near infrared coming out when there was excess heat. And the reason we want to do this is these power gains and energy gains. I can't make that forcefully stated enough. So the question is, how do we activate them? And so when I got my hands on the first one, there's several issues when you deal with nanomaterials. One is they're toxic. You got to be very careful. I've seen people who've worked with these materials who've developed bursitis. You could see the material in their iris, on their cornea. I would say be very wary in dealing with them. And that is why we developed the nanors, because that makes them safe. They're hermetically contained, they're easy to control with the devices we have that drive them, that we'll talk about in the next section. So the question we had initially was, do these zirconium, palladium materials, and here we also looked at palladium nickel mixed together. So do these materials or the deuterated materials have excess energy? Do they have near infrared emission? And additionally, as we'll talk about tomorrow, what is the impact of applied magnetic field intensities, both AC and DC, on them? And what we found, to just quickly summarize, is yes, of course we get heat, we get conventional dissipation. Sometimes we get excess heat, and we'll talk about that. Too often we get an avalanche. Remember, we have these chocolate chip cookie where we have these metallic chocolate chips separated by insulator, and at some voltage we're going to get breakdown. So that's the avalanche that we're talking about here, not a movement of materials, but a sudden electric current that goes through this device. And that creates a paroxysmal electric breakdown. And the reason we see it is that these materials have electrical impedances that can suddenly change from terohms to kiloohms. And so if you're measuring with a current, a Keithley typo ammeter, kiss it goodbye. We've been through a lot of materials here. By the way, with the nanomaterials, let's see if we destroyed this one. We lost more. There was a picture of me with the fusor in Popular Mechanics in 2004, and almost every piece of equipment behind me we destroyed using the nanors in order to learn how to control them. This is the controller we used for the fusor. We use a different one for the nanors. So let's talk about how we measure excess heat. This should be easy for you because it's very similar to what we did for the aqueous system. Here we have parallel diagnostics where we're going to measure heat flow as well as the temperature change, as well as the calorimetry. And we're not happy until all three are identical, showing quantitative match. And also we're not happy if in the pursuit of cold fusion until we see excess heat here, where we've ruled out false positives by time integration and by noise power measurement. And with the NanoR, again, this is what we do. We only showing one of the decorated heat sensors that we put in here. The electric power source can either put electric current through the control, or through the NanoR, or both if we want. And then what we do to look for the magnetic field is we arrange it in a volume, and we'll put the either a DC magnet or an AC magnetic system up above. When we measure input power, as with the aqueous systems, our definition of input power is V times I. The accuracy, obviously, in current measurement is quite good. Our Nyquist measurements, sometimes we go a little bit slower. We're measuring so many things, but usually we're higher than 0.2 hertz at least 24-bit resolution. Okay, our power gain will be defined as the observed output power over input power, but that's an instantaneous measurement. And what we like to do is to do the time integral, where we measure the energy gain, and we always find the energy gain is less than the peak power gain, and you'll see that over and over again. Okay, we can skip this. Our circuits are different. We showed we use a driver. It's really important when you run these materials to understand their electrical properties. So we spent a lot of time building equipment that does that. We call it the NanoR Explorer. This was the first one we made, which we showed at MIT for 5 months. And I'm going to show you the first series 1 and 2 NanoRs, the results of what we saw. And the problem was these avalanches. I'm trying to do 4 terminal measurements here. So the NanoRs in here, we're having there's just thermal wadding here, and we're doing a 4 terminal measurement and some other things as well. So if we look at the impedance in ohms, here it's 3.5 megohms, and we apply a voltage up to 25 volts, and we see that there's an electric current and a normal fall off. Well, I like to do stuff over and over a few times, so we went back, and the 3rd time this happened. When we went up to around 40 volts, here in this one, 23, it varies. Sometimes this can be as high as hundreds of volts. All of a sudden, we see that the resistance crashes. That is an electrical avalanche. And what we see when this electrical avalanche occurs over here, so that the impedance is falling, here's a megohm, here's 10 megohms, and it's dropping down to under 10 kiloohms, we see there's a sudden amount of input power to the material. Looking closer, we see that there's 3 regions. This is the breakdown region. This is the post-breakdown region. This is the pre-breakdown region, and there's some hysteresis. But these are reversible. What we found is that when we get an avalanche, we can, with sufficient time on the order of hours to days, bring it back to where it was before. This just has to do with the loading. Okay, so in review, when we look at these one-dimensional nanomaterial devices, we see they're very high electrical resistances. We see that at a variable voltage here, this group was 24 to 37, but anywhere between 20 and several hundred volts, you get a sudden breakdown. So if you have a current meter that you're using, you've got to put in precautions so you don't blow it out. And if you're running, as we do, up to 4,000 volts, be very careful. Okay. Questions?
You mentioned the electronic response is complicated. Can you expand on that? More than just avalanche? Are there other phenomena?
I will. We will get to that. When it took me 2 years to be able to run a NanoR where we could show the excess heat on one side, go through the avalanche and continue to measure, and it became like an ohmic resistor. That's what we're going to show you. That's the last slide. But it took a long time because in doing it, we would be destroying equipment until I learned how to do it. So. Series 3 NanoRs. So now we know a little bit more about controlling these. And the question was, can we get any that show excess heat? This is the one that first showed a little bit of excess heat. Now, this was nickel with ordinary water. T is the electrolytic, the distilled water that we talked about yesterday that starts off at 18 megohm centimeters, and with equilibration to the air comes down to 1.2. Here's the ohmic control, where we get a match. These two are parallel. It's a tiny amount of excess heat, but enough to put a smile on the face and know at least we're going the right direction. So we made a few more of these Series 3 ones, and we're getting better excess heat here. We're learning how to control it. And this is pre-avalanche. And what we decided to do with one of the first experiments, the late Robert Bass, who sadly died last December, had often suggested what we should try to do in cold fusion is to show that the output linearly increases as we increase the input. And he said it a funny way. He called it the 5 needles. But what he meant was having 5 amounts of input and showing that there's a linear increase. And so we actually finally did that. Here we see the temperature rise as a function of time. This is just the thermometry, ohmic control, NanoR, ohmic control, NanoR. And then when we finally look at the input power normalized delta T, that means we can take the ratio of these two to see our power gain. So we've got a gain of 2 to 3. And so we're getting better. We're learning how, with these Series 3 NanoRs, to learn how to get excess energy out of them. And here, for example, we see, as with the aqueous system, a series of pulses. And slowly, you can't see that too well, but these are parallel over the ohmic control. And we end up getting an excess energy that's almost 2. Again, the excess energy is always a little less than your peak power gain, because you're going to have to average that out, plus there's the duty cycle. Okay, one of the interesting things is we learned which things quench it. I think in doing cold fusion, you want to know what shuts it off as well as what turns it on. So at the end of Series 3, we had finally gotten excess energy out for nanomaterials against an ohmic control, and we learned a lot of lessons. We had confirmed Robert Bass's proof of cold fusion. We learned that there were ways of actually getting the excess heat out. We learned that there's an avalanche breakdown. We learned how to avoid it. And now it was time to do Series 5 and 6. Now these are interesting material. Yeah.
Quick question. When you say beyond ohmic control, what do you mean by that? Because it seemed to me like you were using ohmic control to control it up to the point of destruction of avalanche destruction.
No.
Did I miss that?
No, the controller either puts the electrical energy that's applied either to the ohmic control for calibration, or it puts it to the NanoR. I mean, we've done experiments where it does both, but it just confuses the issue. There's no need to do it, is what we found. So it's either one or the other. Okay. In 5 and 6, we decided we wanted to play around with improving the materials. As you saw in Series 3, we were getting energy gains 2, power gains of 3. So we started to make Series 4 NanoRs. The materials dissolved the NanoRs. We lost a whole lot. Sometimes that happens. It's surprising when you work with materials, they don't always work together and things don't always work out. That's where Series 4 went. 5 did work out quite well, and we ended up bringing Series 6 here for the demo at MIT. So the 5 are like the others, where we're having about 2/3 zirconium, up to 1/3 nickel, and the palladium varies, though some had palladium much higher and 0 nickel. And we have a series of materials now that we're looking at that we decided we would now essentially add more D to more H2 and get the loading up even higher. And those are what the Series 5 and 6 are. And let's look at one of them. So here's a Series 5 NanoR, the second one of the series. This is time. Each of these counts as 7 seconds. You're going to see this over and over. I apologize for it. It should be in seconds. But the way the NanoR Explorer works is you set the amount, time per count. We'll eventually fix it. So it's here, it's each of 7 seconds. So what we're seeing is we're putting into the ohmic control this much power. We're putting into the NanoR this much power. And we're now looking at the input power normalized delta T, which is in red. So we can get the power gain by looking at the ratio of this to this. We're going to be doing this all for the rest of my talk of looking at the nanomaterials. The reason we look at delta T and divide by input power is you can get a rough idea of the power gain by looking at the ratio of the two. So here it's about 7. Now we also, for Series 5, had begun routinely adding heat flow because we want to see that we're not getting 1 and 0 or minus on the other. And here it's true. We're also getting gain as determined by a completely different sensor. So here's our input to the ohmic control, same experiment, input to the NanoR. These are calibration pulses. So what we do is we have a ohmic control, a series of calibration pulses, and the NanoR here in green, and our heat flow divided by input power is in green. Is in red. So we can take the ratio of this to get the power gain is determined by heat flow. And here too, we see this corroborates the delta T measurement with completely different sensor. Here's the calorimetry, a third way of looking at the excess energy if it exists. So here's our ohmic control. Here's what we measure coming off it for heat. Here's what we put into the NanoR. Here's what we measure for the heat coming off. Here, to measure the power gain, we take the ratio of this to this. But only for the calorimetry. All the others are one to the other. So here we're not completely capturing it all, which means this is an understatement. We're getting more out. The amount we calculate is going to be a lower limit because we're not capturing it all here. Here too, in the calibration pulse, we're not capturing it all. So therefore, we're not capturing all of this either. Again, it's a lower limit. Questions? Okay, let's look at how the impedance changes as a function of time. The ohmic control, well, it's what we expect from an ohmic control. It's a straight line. And then the NanoR is a bit of a problem, isn't it? Here, it's, I think these are in kiloohms. So we're running about 1.2 megohms, and we end up coming down to, at the end here, 200 kiloohms. That is why it's so hard to control these, is that we're not dealing with something with a fixed impedance. Let's look, we made another one, 5.3. I'll just run through a few of these. Input to the ohmic control, output, that's the core temperature, here's the heat flow. So if we look at the heat flow divided by the input power, such as here, the ratio of the orange to orange gives us our excess power gain. Pretty good, it's much better than 2. Here, here is the delta T normalized to input power. Again, we take the ratio here, and again, we've got a nice ratio of about 3.5. We'll skip that. That's for the advanced course. We'll skip that. Let's jump ahead a little bit. By the time we got to this number, here's our ohmic control. Here's our input power to the ohmic control at 2 levels. Here's our input power to the NanoR at 4 levels. And the ratio of our power gain then is this to this, because it's delta T over input power. Okay, so we clearly, with the nanomaterials, are getting reproducible, controllable power gain every time we put the electricity in. Okay, I mean, there's so many I could just keep running through. Here's another one. This was 24. Here's our ohmic control. Notice we're not getting the whole amount. So when we look at the nano, we're actually going to be getting more. This is complete calorimetry. Power on this side, energy on that side. So the ratio is this to this. But since we're not getting complete capture, you know this is going to be a lower limit. Questions?
Is there anything not obvious here that accounts for the rising powers in those 4 step functions?
Yes, this was the one that had the polarization effects. This is a different. We are learning as we do this. Certain of the materials have very interesting ferroelectric and then ferromagnetic effects. So I think that's what it is. That was a good pickup on your part.
Another question. Myself.
Yeah. In fact, we saw it here as a continued increase in excess energy. With a lot of our systems, we've never driven them as hard as we could. I pointed that out with the aqueous systems, and here too we see it with the nanomaterial. Yeah.
Sorry. Were you able to do SEM work on the particles?
Not yet. It's all of that's in progress.
Okay.
Okay, let me go up to 6. Any questions on 5?
You mentioned that there's different things that you learn to quench the process like silver, and what other things are quenching agents?
What a good question. We talk about more of those at the advanced course, and give me a call and we'll talk about it. Those are really important issues. All right, nanotech milestones. I showed you that the first series 1 and 2, we discovered that there's electrical avalanches. When we went to series 3 and 4, we got near reproducible low-level excess energy. Series 5, we had them preloaded. We showed you good energy gain. It was reproducible. Series 6, we started hyperloading them. And that was the one that we ended up bringing to the open demonstration at MIT. And we took some of them, we made them into what we'll call M-nanors, magnetically activated nanors. And we'll talk about that tomorrow. And I showed you that some of the M-nanors are really interesting because they are emitting things that we can pick up on CR39, like I showed you yesterday. And then we'll show you the Series 7 nanors, where we started exploring new materials and we tried to improve our hyperloading. Okay. All right, here's our first. This is just thermometry. Again, it's hard to see stuff with just delta T. You want to take the delta T and divide by the input power, where we do it here. So this one, see, becomes a flat line. How nice that is. And this one won't become a flat line because of optimal operating points, but that's okay. Just as it's not a constant impedance like the control, it has information in it. So here, in looking at this is 633, this is a different one. We're looking at our input power, normalized delta T. So this is delta T over input power. So we can take the ratio of this to this for our power gain. And that's a pretty good number. This was January 22nd. So I called up Peter. I said, I think we want to take a demo to the course. This is looking really good. And here is our calorimetry of that run. Here's our input to the ohmic control. Here's our output, slightly less. So when we take this ratio, it's actually going to be a lower limit. If we integrate it, which we must do to rule out false positives, we get a nice match here, as we would expect. And we get a superlinear rise of energy for the cold fusion device. You get a little bit of heat after death here. And what we see is that this difference is, actually this difference is our excess energy gain, and this little difference is heat after death. Here's our calibration post. Questions? Let's keep going. So we had the demo, great class, and during the class, I wasn't sure if it was going to run because when you move stuff, half the time you screw up the experiment. You better either have 2 of them or practice. When we did the initial aqueous demo in 2003, coming here we had no trouble. We showed the excess heat, and going back, all of the heavy water spilled. So I realized how lucky I was that it hadn't happened coming. It did work. This was during the class on the 5th day. Here is our input power in blue to the control. Here's our input power in green to the NanoR. And this was the temperature that we measured. Okay, let's divide by input power. So this becomes a straight line. And now we can take the ratio of this to this. And here's our calorimetry. That's the control. Here is our NanoR. We take the ratio of this to this. That's our power gain at each of these levels. And here's what we found. So the power gain during the class, we had a gain of about 13, 14 times input. By heat flow, every time we do heat flow, for some reason when we move the device, the first experiment never works. And then finally things stabilize and we get it out. So it didn't work the first day. And by calorimetry, we saw similar amounts of excess energy. And the energy gain was 14. And we continued to run it. For example, that evening, here's our ohmic control. Here's our NanoR, ohmic control, NanoR. Notice the fall off. Now here we're taking the input power and dividing it into the delta T. So we can take the ratio. See the fall off? This is the heat flow. Not quite a fall off. I mean, there's a little jump there. But this is our power gain as determined by heat flow. Here's our power gain as determined by the calorimetry. Match for the ohmic controls. I didn't label them all. Here's our NanoR. We're getting more out than we put in. And our total energy gain is here. We put in this much energy, we gain that much energy. And again, notice the fall off. So we have 3 different ways. We get a total energy gain of just under 5. We keep running, we do another day. And there's more and more of this. Now here we're putting input power to the control, to the NanoR, to both of them, to the control, to the NanoR. I mean, it's horrible. You end up taking delta T normalized input power, so your ratio is this to this, and your ratio of both is to this. So you're losing it. You're losing all your signal by doing, which makes sense. I mean, if you're putting it in the control, you're diluting out the amount of power. So we tried it. We never went and did that again. Doesn't make sense. But here it is with the heat flow. Here it is with the calorimetry. And then I didn't like the both. It's just nothing to be gained from it. We went back to using the control in the NanoR. And here we see we're up to February 7th. We ran this for 5 months. I mean, people say cold fusion is not reproducible. How many months do you need? How many cycles do you need? How many duty cycles? So here's the control, NanoR, control, NanoR. I mean, NanoR control. And here by heat flow, it's the same. We take the ratio, and Peter said, let's try a different protocol. Let's have it increase the time between the measurements. So here we see the input to the ohmic control. We wait amount of time. We put input to the NanoR. Ohmic control, there's our calibration pulses. Ohmic control. This is delta T. We have to do it normalized. Now it's normalized input power, so we can take the ratio. And this is our gain. So it really doesn't matter if it's separated in time. We're still getting power gain out. And it was a good hypothesis, but it doesn't seem to change it. We still see power gain by delta T normalized. We still see power gain by heat flow normalized. And we still see power gain by calorimetry. And here again, we don't capture the whole amount, so this is going to be a lower limit. Yeah.
And Joel, there wasn't a hypothesis that there were 2 issues. One is when you do your runs, you go sufficiently fast that oftentimes your calorimeter doesn't equilibrate. And the other issue is that if you stretch things out, that you're looking data, there's a better chance you can get a referee to improve it if you try to publish.
All good reasons. Thank you. And there was a third reason, which was we discovered this. We had a catastrophic event. I don't mind pushing stuff and breaking them. Maybe it's the old training here from MIT going back to the 60s. So for example, as we raised the power on this, we actually lost the excess heat. This is delta T normalized input power, and we had a perforation through it. And what happened was, for whatever reason, here we're having power gain, and it comes down to being like a resistor. It's not as good as we got to do later, but here you see it too. It's a loss of power gain. If this hadn't failed, it would have come right across. Instead, it comes down to here, to another resistor, with a little bit of unscheduled heat release. So something kept happening after. There's a lot of material physics here. We don't have it totally controlled. And a lot to discover. Okay, we took the devices over to a second location. We've now left MIT, and we are at my office in NATIC, and we're going to put them under magnetic fields of 2 Tesla that we flip every 10th millisecond. And that's enough at 5 centimeters to generate about 40,000 volts per meter. And here, what we see, this is just input power and delta T, so you can't take the ratio yet. Here's the heat flow normalized to delta T, so we can't take the ratio. And heat flow normalized to delta T, and here's the calorimetry. So this is 4 months after we ran at MIT open continuously. Not 100% duty cycle, but more than 10 or 15%. And we take it to a second location. And the reason we were doing this was calibration for what you'll see tomorrow, which are the magnetic experiments. And this is a year later. This is November, and we're still getting excess heat out. Here is the input power to the ohmic control. Here's the input power to the NanoR. This is input power normalized to delta T normalized input power. So we take the ratio, and we're still getting a nice power gain out. And the reason this is so high is this is an MNOR now. This is one that we've treated with the magnetic field. And here, this is a year later, and we're still getting power out. What are the implications? 1, we have a dry cold fusion system. We'd never had one before. 2, we're getting pretty good energy gains, much higher than we ever got with the aqueous. We're getting energy gains of 20 and plus, and over several months. We are getting them with a variety of materials. We found that our hyperloading system works for a number of materials, and we're looking for new ones we're trying to investigate. One of the things we never told anybody initially was the amount of active material was only 50 milligrams in that device. Ran for months. And we showed the results at ICCF 17. Questions? All right, I'll show you one more segment. Okay, Series 7. We took everything we learned from the past ones and decided to make some new ones. And tried all kinds of different materials. Again, just to review what we have here, we use calibration pulses where we make sure, I don't trust the computer, the DAC. I want to see a couple of meters calibrated, and that's what these calibration pulses are for. So here is our input to the control, our output to the control, our input to the NanoR, our output to the NanoR, and our ratio is excess power, and that's a pretty good number. So we like the Series 7. Here's the second one we made. It's opposite a wire wound ohmic control, and here's the input to the control. This is the temperature. Here's the input to here. Here's the temperature to the NanoR. And we can take the ratio and see the power gain. Again, we see these are working pretty well. At low power, we're getting very high outputs. In fact, when the input power was a tenth of a milliwatt, we're getting power gains of 100. By the time we come up to half a watt, our power gain is 3.5, 3.3. And remember, the optimal operating point comes down. So for this NanoR 7.4, it came down to 1, just like an ohmic resistor at 1.5. So as long as this particular NanoR, as long as we drive it at less than 1.5 watts, we're getting energy out at all levels. So here's 7.4. This is the input to the NanoR, the input to the control, the ratio is our excess power, and that's more than an order of magnitude. That's pretty good. But again, these are low power we're driving them at, and it's reproducible. Here again, we're looking at input power normalized, so we can take the ratio. Here's our input to the NanoR. Here's our input to the ohmic control. We really want these to overlap. It's not always easy to do. Again, I told you that unlike an ohmic resistor, where you read the bands or you measure it a priori and you know what it is, these little puppies change with time. But again, for being a close match, these ratios are going to be our excess power. Here we're looking, again, input to the NanoR, input to the control ratio is our gain. Okay, this is our calibration pulse, ohmic control, NanoR. I like to bracket it. Here's another calibration pulse, ohmic control, NanoR, and the ratio that we want to take are these two. This is the delta T over the input power. And that's a pretty good number. These are numbers such that we may be able to hit home plate. And that's what we're looking for. A couple of important points about NanoR 7.4, we went over 1 watt. I mean, previously with the 6 NanoRs, they went up to 0.5 watt, but most of them were running at a 10th watt. So we're moving up in power with the new ones. Here in this run, this is the NanoR. You can't even make out what we're putting into the NanoR here. Is the control and the ratio is the gain. Now this one's interesting, 7.7. This is a nickel deuterium NanoR. I mean, a lot of people talk about nickel and hydrogen, and we do get out excess energy, as I showed you, with nickel in ordinary water. And when we pepper the water, when we increase the deuterium in the water, we find we get more excess heat out in aqueous systems. So I was very interested in what we see here. And in fact, what we see is excess power. And here we're driving at 370 volts. This is our calibration pulses. We do 1 calibration pulse to the ohmic control, a calibration pulse to the NanoR. Here we're dumping power into the ohmic control, power into the NanoR, and that's good. There's a good overlap here. And we're just looking at delta T. So remember, to get the power up, we got to take and divide by delta T over P in. So here is our power in to the ohmic control. Here is our power into the NanoR, and our ratio is this. That is our power gain. We did get power gain. The bottom line is from this nickel and nanomaterial and deuterium. Here, for example, we see the delta T. So for the ohmic control, it's going to rise. We're not going to get a straight line unless we divide by input power, which we do here. And I think our straight line is right here, actually. This is the power into the control. Here's our power into the NanoR. So the ratio, the power gain, is going to be this to this. And these are log units. So we're doing better than 100. And are we seeing that also with heat flow? Yes, we are. If we take the heat flow measurement and divide by power in, here's the heat flow over power in for the NanoR, heat flow over power in for the ohmic control, which again comes out to be a straight line. And this ratio is our power gain. And that's more than 2 orders of magnitude. Now, 7.7 was the first one where we learned there's a new control. And this will be my last set of slides before Peter takes over after our break. And that is, we like to see that in our calorimeter, it's accurate. We want to see that when we put a square wave in, we get a square wave out. We want to control so that we're able to calibrate and know we have excess energy. And here's a new control that I think is really important. Can we tweak the nanomaterial or cold fusion system so that it becomes non-over unity? And that way calibrate our system. So here, in fact, we do that. This is like, for me, chasing a tiger. It took 2 years, lots of lost equipment. But in the end, I got my photograph and bagged the breakdown. And here you see, here's a pre-avalanche. Here's post-avalanche. So this is the power into the control, the power into the NanoR, which after the avalanche goes way up, because remember, this is a log scale. And here is our delta T. This is just delta T, not dividing by power in, which we do here. And here is bagging the avalanche. Here is our calibration pulse, not a calibration pulse. Here's the ohmic control. Here is our input power to the NanoR over many ranges. And here is our delta T divided by input power, which then continues here. This ratio is our power gain. We're getting excess energy, excess energy, excess energy, excess energy. Goes through the avalanche, it's an ohmic control.
That's really convincing.
It is another way of proving that we have a good system that we can trust, that our calibrations are good. And this system, the same thing happened with the flow, though it even went down more, but it went at least down to the ohmic control. See here, if we look at heat flow normalized by input power, this is our ohmic control, here's our NanoR. We're always getting excess gain out until here. Post-avalanche, it goes to here below 0. Now here's the calorimetry. The ohmic control, we get a match, a slight lag. These are parallel like we expect. Here's our NanoR. We're getting a superlinear rise. When we go post-avalanche, notice they're parallel again. It's an ohmic control. Yeah.
On your previous slide, go back one slide. If I'm looking at your post-avalanche thing, so this is relative heat flow normalized to the input. So I should be looking at the ratio of that one to the blue one to see the gain.
I expected it to be the same. In fact, it's less.
It's less, but it looks like it's a factor of 5 less. So do you interpret that as either doing work on the NanoR, or is this an inefficiency for your heat flow measurement?
Or a non-equilibrium of the heat flow. Maybe something has changed. The heat flow sensors are harder to work with than thermocouples or thermistors. When you have a sudden change, they don't work well, right? So probably to answer your question, we should let this run out.
I apologize. I want to press the point and understand it. Is your NanoR next to the resistor?
Yes.
In this configuration?
Yes.
So the resistor measurement, the heat flow measurement for the resistor is using basically a very similar geometry with the same heat
Identical.
flow, yeah, same heat flow sensor.
Yes.
So in this other case, the conclusion one might come to is that some of the energy is actually not going to see through heat flow sensor, but it's, I mean, if it's not going any place else to go, it's going into doing work or damage on your NanoR or something.
Or the ohmic control. There's other structures around that may be involved. They'd have to.
Is that less heat than the control is emitted after the avalanche?
Heat flow. It is less heat flow than the ohmic control here.
Would that be considered negative heat, or let's understand that?
I think if for it to go negative, it's got to go here. It's just not flowing. We're just not getting heat out. Something has changed. It was gushing out like a gout, and now it's clotted. Something. I mean, that's a bad analogy.
Did you have a temperature sensor in your NanoR and resistor for this experiment?
Yes,
Do you have the data for that?
yes, here. And here's the raw data. This is the temperature data divided by input power. This is the raw temperature data.
Okay, so the temperature is actually higher.
The temperature is higher post-avalanche.
Because you're putting in more power, in this case by a lot, so because it's so much hotter, you've got other heat flow.
You know, that may be another issue. It may be that in the absence of cold fusion where you're getting more out, the heat flow is not, the sensor is not as efficient. We may be dealing, it may be that a lot of good questions come out of it.
It seems like that would be something to spend some debugging time on.
We will. Yes,
Were you able to do calorimetry on this sensor?
here. Here's the calorimetry. We do a match for the ohmic control. For this run, I mean, we have a lot for the sensor, and I mean for the device. And here is pre-avalanche. Notice as we increase the input power, it's the optimal operating point, it's falling down. Suddenly we go through avalanche, and
So since your calorimetry is in power balance, it's arguing that you're not losing the energy during work on
Right.
the innards. Your heat flow sensors got some kind of non-linear temperature or something.
or the heat staying here and not going up the heat flow. I mean, it's got to sum up to the constant. So if we're seeing it here, we can't go up the heat flow device.
Thank you.
Here we can actually show the power gain as a function of time. So this is one, this is break even. And within the limits of our measurement, we're getting a nice power gain here. And it comes down to 2 just before the avalanche. And we just maybe within the margin of error have a very slight amount of excess heat just post-avalanche. And there's our calibration pulse. Questions? All right, we're almost done. These are just a few more of 7.7. Again, I think the point I wanted to show was it came back. See, this is November 7th. I told you that the breakdown of these materials is reversible post-avalanche. That's why I'm throwing these second slides in. But it takes a few days. Here is November 13th, and we're getting excess heat again. So here's our calibration pulses. Here's our input to the ohmic control. Here's our input to the NanoR. And we can take these ratios to get the power gain. So we're back. It has taken a while, but it is now active again.
That's very weird.
Is it a case that the device was just sitting idle for that week in between?
Yes. At the end of the day, this was what we saw at less than 1/10 of a milliwatt. Here too, we were getting a power gain of 100. At 1/4 of a watt, we were down to a power gain of 6. It fell to 3 at just under half a watt.
What's your optimal operating point, power point for that unit?
I don't have the slide here for that. But I mean, you can actually get it from here.
Yeah, it looks like it's very low.
Several of them have enough measurements where you can get it right off the slide. This was 7.8. Let me show you this one.
The calorimeter, paraffin?
This one is a zirconium oxide palladium. And here's our input to the control. Here's our input to the NanoR. And I think these are just raw heat flow and temperature. So let's divide by the power in. So our input power is here. This is the power to the control. Here is our power to the NanoR. And these ratios are our power gain then. So we've got a couple orders of magnitude here. At low input power. This was the mode D device. Most cold fusion systems that we have an activation current. before they turn on. Mode B seem to turn on right away, and you just keep losing. So the reason I'm showing you 7A is it has very high power gain initially. Here by heat flow, this is the ratio. So we've got a power gain here, and that's a log table. Here too, this is good because there's overlap. That's what we want to see for the input powers. Input to the ohmic control, input to the NanoR, and this ratio is our power gain here by delta T. And you can see it's more than 2 orders of magnitude. That same run, we look at heat flow, and this too is order of magnitude and a half. Here's the calorimetry. We see the noise level. We can see the input matches the output for the ohmic control. For the NanoR, here's our input, here's our output. So in terms of our NanoR summary, first NanoRs, we discovered the avalanche. Series 3 and 4, we learned how to get just a little bit of excess energy out. 5, we were getting gains of 7. Series 6, we showed at MIT, we had power gains of So we now have NanoRs for the first time that can handle more than a watt compared to last year, a tenth of that. We're getting up to 20, even in these, we're getting up to 27 times output for low input power. And we have finally shown the breakdown on both sides. We've imaged both sides of the avalanche. And that took a long time to do, but I think it was really important to chase. And these are our results for the NanoR. Here's zirconium PD. And then we learned how to make the Series 3s, Series 5, Series 6 is what we'll talk about tomorrow. And some of these are the Mode B devices, and they have very high power gains. And if we could figure out how to drive these at the 1 watt level, we hit home plate. So, NanoRs, very effective way to make clean energy, very efficient, very reproducible. We have confirmed and verified that they're making excess energy several ways, including delta T, including heat flow, including calorimetry. This year we'll be adding the other serial techniques of propulsion and electricity like we did with the aqueous systems. Thank you. And I think that's it for today. Questions?
How are you doing your heat out? How are you doing your heat out? In your aqueous system, you have water bath around it or some bath around it?
A good question. Good question. We use a big thermal block. In fact, what I do is I try to use very good geometry. So we build our calorimeters. Think of it as if you're doing an optical experiment. We'll use fire bricks. We'll get the heat to go in one direction. Okay. Then we'll put in a heat flow sensor, variable thermal resistance, and then put it into a big metallic object to get to drive the photons in that direction. And it works really well. Once we got rid of the pi r, the 4/3 pi r cubed, we got even better measurements. Any other questions? Why don't we take a 10-minute break and Peter will come in. Jerry, want to cut it?
I'll stop. I'm going to stop it here. I'm going to stop the broadcast here for the break, and then we'll pick up another one. So.
Thanks.
Tune back in.
Oh, yeah.
gave all you guys a big break. I had so much data from the NanoRs. It used to be terrible. We come in, I mean, even now it's too much stuff. But it's just amazing. We just collected all the data over months and months and months. And it's really the same thing like the propulsion device. It's really used. 150 runs. I will show you one or two of them right in this It was nice, doesn't it?
since I speak so softly, did you want to put a microphone close?
Maybe I'll film that. Just-
Are you already on?
We're back. I muted the microphone when we were at lunch break.
Usually.
I'll put this one up here. Really, if you want to move it even closer a little bit, right on the edge of the table. That way, if there is audio issues, I can resync that audio with it later.
Thanks. Okay. Welcome to second talk delivery. As usual, my presentation will begin with a warning. Working in the field is not the safest thing to do for a scientist these days. Last 2 days we've covered a huge amount of ground. Yesterday we were interested in issues as to how to get high D to PD loading, because we saw that that was a requirement for CNSSE. It's not the easiest thing. We saw day one that the chemical potential was very high, which tells you it's hard to get it in. With respect to the practical issues, we compared experimental loading curves against former TAFL models. We found that in order to account for the earlier literature, which got low loading, versus the cold fusion experiments, which get very high loading, we had to posit that there are massive internal leaks in your average palladium cathode. And in order to get high loading, you have to do something about those internal leaks. Our next step in this was to make our first theoretical ansatz, and that was the notion that you wanted to make a molecular D2 system. We found initially that there was no way to get D2 into palladium deuteride because the electron was too high. We made use of ideas from embedded atom models in order to understand helium first, because it's simpler, and then hydrogen in materials. So the issue is electron density. Electron density is too high. In order to reduce the electron density, we need to work with a monovacancy or other structures, defect structures that give lower electron density. But my focus has been on the monovacancy since it's simple and theoretically of interest. So the idea is that, following from the literature, is that you can make D2 of the loadings high enough such that the other octahedral sites around a vacancy are filled. We did an awful lot of stuff. We found that in the literature, there's an analog. There's a molecular H2 state that's been studied experimentally and theoretically on a clean palladium surface where the palladium is loaded. So this is PD201, this is PDH 201. We argued that the requirement of 0.83 or so loading or higher at the time you produce excess heat might be a consequence of needing to produce molecular deuterium within the vacancy. And the statistical mechanics model for that seems to match the observed excess heat curves, at least qualitatively. We saw that making vacancies is not the easiest thing to do. If you are at high loading, vacancies get stabilized near a loading of 0.95, and we noticed that a loading of 0.95 sometimes during the loading history was a requirement found at SRI for the production of excess heat in the Flesch and Pons experiment. Conjecture was that this is the reason for it. Now, the vacancies don't, or you can make the vacancy phase if you can arrange for diffusion. So if you go to high temperature like Fukai and Okuma back in 1994, but at room temperature, the vacancies don't diffuse. So you can, if you're patient, you're willing to wait some millions of years, probably you can get the vacancies to propagate in and work. But if you're less patient, then you're out of luck. You've got to do something different. One possibility is to do co-deposition at high current density, so you get a high surface load, and when the co-deposition occurs, you make this high phase with superabundant vacancies. So that's the conjecture as to how the Fleisch-and-Pons experiment works. In the Fleisch-and-Pons experiment, the co-deposition would be inadvertent. Generally, it's an uncontrolled process. So today, we've got a lot of goals, but our initial goal is to begin to make a little bit more progress on what's going on microscopically. Namely, we argued in the first day that there's a lot of skepticism that excess heat in cold fusion could be real, in part because it's not consistent with known solid state and nuclear theory and early experiments. The argument was also that the effect was not reproducible, but we went and we looked at the negative experimental papers, and we found that the case for non-reproducibility was very much overstated, that the negative experimental papers leave an awful lot to be desired. So, so we worked with the ansatz that we needed D2. Underlying this is the beginning of a naive picture where the D2 reacts in some way that will be of interest shortly, but isn't of interest quite yet, to make helium-4. So the experiment implicates the presence of helium-4 in connection with the energy produced. So our attention is going to be focused to the helium-4 problem for a while. Products. So normally if you're doing chemistry, if you burn something like methane, you have chemical reactions. So you start with methane, you start with oxygen, and you end up with carbon dioxide and water, plus you get a fair amount of energy out. What that means is that you have a fuel and you've got chemical products. The chemical products, after a long time of a lot of work in chemistry some centuries ago, you get products in commensurate amount that you can measure. And there's a lot of them. In this particular case, if we go after the 630 kilojoule number, which was the number from Fleisch-and-Pons' 1990 paper, we're getting on the order of a mole of CO2 and twice that of H2O, which is a fair amount of products, which is in general easy to see. So commensurate chemical products in connection with the cold fusion experiment, if they were present, would be straightforward to find. However, they're not there, which is why Fleischmann proposed that we were dealing with a nuclear process. If we were dealing with normal hot fusion type reactions, we would expect neutrons coming out, we would expect some tritium. If there was tritium produced, we'd be able to see that. It's not a particularly difficult amount of tritium to find. The neutrons is more important, at least in terms of the energy deposition into the body. Motion sickness sets in near 0.5 to 1 gray, and so joule per kilogram. So if you're making lots and lots of joules and the energy is coming out as neutrons, you can get sick pretty fast if the neutrons are there. If neutrons aren't there, measurements with much more sensitive neutron detectors and other nuclear detectors are not showing neutrons or other nuclear products. So the question is, what should we look for? The issue is, with respect to the nuclear products, is that you don't, if they're not energetic, it makes them hard to see because there's not very many of them. And they're hiding in a lot of other stuff. So for example, if you had 630 kilojoules, and if we took some random nuclear number, which is D2 to helium-4 mass energy difference, 24 MeV, this would give us about 10 to the 17th atoms. And once you get down to 10 to 17 atoms, it's a little bit more difficult to find such a relatively small number of atoms. Okay, in the early days of the field, having been there and been in the lab and been talking to people doing these searches, the question is, what the heck should we look for? And quite a few searches were done. Helium-4 was looked for initially. We didn't know that Fleischmann had been measuring helium-4 in the gas in those days. This was not public information. But people were looking for isotopic changes in palladium, lithium, and looking for elemental and isotopic anomalies involving other elements. A lot of time was spent on these searches, a lot of money was spent on these searches, and a lot of negative results were found. Various minor elemental isotopic anomalies were found, but none of them seemed to be correlated with heat, and none of them were clearly anomalous. But what we would have loved to have had with a nice, very radioactive product that was sitting there. All you had to do was bring some X-ray film, you could see it easily. That wasn't what turned out to be.
There's the helium information flashed in the since become public information.
You know, I can't remember that I've seen a publication discussing this. But people
I think it might
have
have helped in the fray back in the early days.
it would have helped tremendously in the fray back in the early days. So I don't have a published reference for it.
Okay.
I mean, after other people found it, we heard that Fleischmann had known about this all along and chosen not to share information. So as is known at this point, helium-4 appears in the experiments in the gas phase in amounts correlated with the energy, amounts commensurate with the energy produced, and amounts correlated with the energy. But let's take a step back. So there was discussion in 1989 that helium-4 was the result from the process that was responsible for excess heat. So Fleischmann conjectured that deuterium was involved. There was discussion that helium-4 was involved. So naturally, the physicists said, well, let's think about D plus D going to helium-4. That would give us, according to what's measured in nuclear laboratories, that reaction can happen with 24 MeV gamma coming out. So there's lots of issues. There were searches for helium-4 in the cathodes themselves, and those searches came up with negative results. There's a theoretical problem because in the Fleischmann-Pons experiment, there's no 24 MeV gammas are coming out in amounts commensurate with the energy produced. And there have been a small number of searches with detectors that would have been capable of registering it, resolving 24 MeV gamma. But the bigger issue is that if you were getting lots of 24 MeV gammas and you were standing next to it, after a relatively short time, you would know. So they're not there. Let me, one of my friends years ago did some measurements for the 24 MeV gamma using the sodium iodide detector. And you can see there's some counts there, which are at your 24 MeV, which are the gammas from diffusion reactions. You look at this and you say, well, it's a relatively weak signal. The answer is, well, yes, it's a very weak signal. And the reason it's weak is because to get a gamma out, it's an electromagnetic process. And it's competing against the 2 plus 2 going to 3 plus 1 products, which is mediated by the strong force, which is ordered magnitude stronger. So measurements have been done for collisions of 2 deuterons to measure the efficiency of the 24 MeV gamma reduction. So compared against some calculation, E2 plus M1 measurement, E2 mechanism. This is the electric quadrupole magnetic dipole. And this line is going up, so if you're at 0 energy, you'd expect a number somewhere around here as being the efficiency for making gamma. And here we go. You get roughly 50-50 for the primary hot fusion reaction products. And for the gamma product, your efficiency is down by orders of magnitude. This relative ratio prompted Heisenga to postulate his third miracle objection that normally diffusion gives you 3 plus 1 products. If people are claiming you get helium-4, if you look at this, it's very unlikely. So Heisenga was arguing you have to find some way to suppress these guys and have this come out and be dominant. And again, because the four NAND system is so simple and just so well done, there's no possibility of doing that for an infinite reaction. So if you're going to do an experiment and look for helium-4 in the gas, you got to detect it. And the headache is that the mass of helium-4 here is not too terribly different from the mass of D2, unless you've got a good mass spectrometer with good resolution. And if you arrange for the D2 to be in amounts present commensurable with the helium-4, for example, normally in the outgassing in electrochemicals, large amounts of D2 because you're doing electrolysis. The amount of helium-4 you get is a very tiny amount. So you start out in an electrochemical experiment with this being very large and this being very small. And so the wings of this interfere. So it's not an easy thing to do to collect the gas and separate it out and do a measurement. You have another issue that helium tends to leak through pretty much everything. So you have to work with special helium link tight stainless steel and other helium link tight materials in order to collect the helium and not have contamination come into the air. So a headache is air contains helium-4. And in some experiments, the amount of helium-4 you make isn't all that much, so if air leaks in, or if you've made it, you have to be able to distinguish between what you've made and what's leaked in. Ideally, you'd like none to leak in, you'd like the make to be much more than the atmospheric concentration. Anyway, not the world's easiest thing to do. It's a headache. And, but it was done. And the way it was done is an expert on the cold fusion part of the problem, Bill Miles, who had seen excess heat in a number of experiments, gathered together with Ben Bush and Hagelstein, who were specialists with respect to helium detection. And they put together some helium leak tight systems. Here's the cell, sample flask, and so forth. Then they you need some equipment in order to reduce the amount of deuterium relative to the amount of helium. I'm going to assume that's what this is about. Runs were done with light water experiments, so light water tended not to produce very much heat, so they used this as a control. So no helium-3 or helium-4 was observed in any of their light water runs. They did heavy water runs, and in this case, they saw, in some experiments, they saw some excess heat, and in connection with, and correlated with the excess energy produced was helium-4 observed. Although the agreement's not perfect, for example, here's one where it looks like you've got some excess heat, but no helium-4 or helium-3 is observed. So these early experiments pointed the way to their good effect. But if it's going to be real, you'd like to have it happen every time. You'd like to have the amount be the right amount and so forth. This is an incredibly important result. And as an initial measurement, it had its flaws, but its significance is maintained on the line. The experiment which kind of knocked me off my seat with respect to helium correlation with excess power was one reported by Gotzi and his co-workers at one of the ICCF conferences. And they've reported on this system for a number of years. At one of the earlier conferences, they talked about this system and how they were debugging it. And they were running to see if they got neon in the system as a way to test for atmospheric contamination and so forth. So what they had, I'm looking at this and I'm not sure I'm seeing it, but they had this very large torus with a large number of experiments in it, which will become important to us again tomorrow, I think. And in one of the cells, they went and put some helium leak tight, built a helium leak tight system around it. They collected the gas. But they did it different than Miles and Bush and Hagelstein. They had a time resolution in their system. So, for example, here's a test. some helium is introduced at T equals 0, and then measurements are done at subsequent times. And you can see that the helium that was put into the system comes out over time. And if you look at this, you say, well, a few hundred seconds, that's not such fast time response. But on the other hand, it's going to be very, very fantastic time response relative to the time scale of the experiment, which is measured in hours, hundreds of hours, and so forth. So here's the data. I got to see this with the color view graph with the where the correlation between the bursts and the helium was a little bit clearer even. I mean, it's reasonably clear here, but it was even more impressive. So on this scale is, so here's time in hours. There's a long time scale. Here's the scale in watts. And so here's an excess heat burst, here's an excess heat burst, here's an excess heat burst. So time starting along this way. So this one, this one, this one, this one. And what you're seeing in connection with the excess heat burst is you're seeing some helium. Another heat burst, you got helium, you got more excess heat, you got helium, you got nothing, you get nothing, you get excess heat burst, you get a helium signal. And this was stunning. The time correlation between excess power that produced in Helium-4 signals. For me, this went a very long ways towards having me believe that maybe this is real. Namely, in Miles, the Bush-Lugowski-Miles experiment, the excess heat wasn't so large, it was a small factor, but helium was sort of here or there and varied by sort of like a qualitative measurement. I wasn't really all that convinced. It was, again, important experiment, but in terms of its persuasive ability, it wasn't as much as what you like. And I saw this, and I thought, okay, I'm starting to believe that maybe this is real. Again, wanting to see more experimental data, wanting to see more results. It would be really nice if somebody had a system set up to do this in this day and age. Of course, there are no resources in the field at this point, so we can't do it. But you know, a fantasy might be to take a nano, put a helium leak tight system with helium, time resolved helium collection, turn it on, produce heat. The thought is Mitchell's devices are deuterium-based devices, so they probably work like this. Probably would be able to produce helium on command. Probably produce a lot of helium on command. You turn it on, turn it off, turn it on, turn it off, correlate the amount, correlate the time. You have a very crazy experiment. It would be very important result.
Well, that's all more expensive, isn't it, to do that? I mean, if you had the device, how hard is it to measure the helium? More expensive is it to measure the helium?
Probably, if I were going to do it the way I would want to do it is work with a facility that has good resolution Helium-4 detectors, and there are many. There are a number of them around within our community. SRI actually has one in the lab.
Is Mike really doing that with the Brillion? They're doing that with the Brillion reactor?
This is unknown to me.
So I visited a year ago. They were looking for something. It might have been Helium-4, and they had it.
Yeah, at the time they were looking for something else for another experiment.
Is it expensive equipment?
Well, their mass spec was somewhere between, I think it was on the order of $2 million for the mass spec, and that was, I don't know, 15 years ago or something. So they're pricey. But if you like, it would be better to work with one that exists. People have expertise using it and running it, and then bring your sample to the system. That would be the better way.
As an example, how many are here at MIT that you know?
I don't know how many are at MIT, but being at MIT, there is no chance that you could bring a cold fusion sample and ask.
I'm just curious, like, are there any lab?
Again, it just doesn't matter. The antagonism to cold fusion at MIT is so strong. There is no way at all to get a Helium-4 measurement done at MIT at this time. Even talking about getting you excused from the office at Hagelstein. Okay, so we've got initial observation of helium correlated with excess power, and I've got an experiment that's actually showing time correlation. What we'd like more, but I suppose it's time for me to pause and catch my breath. So energy has to be associated with the product. You don't get energy like for nothing out of the ether. No chemical products, because we would have seen them, we'd be sure. No energetic nuclear products, but we're getting helium-4 in amounts commensurate with the energy. We're getting it time correlated. And I note that to contemplate helium-4 as a product, in this case, perhaps DD reacting to make helium-4 without gammas. Again, there are no gammas in these experiments. This is completely inconsistent with nuclear physics. And the physics folks would like throw you out the window for even contemplating that something like this. Ross and Kevin, are there comments or thoughts, questions? Yeah.
In your view, is it this problem right here that requires quote-unquote new physics that's the biggest barrier we have?
Yeah, it's the generic problem. If you believe that you're getting nuclear energy, if the energy measured in these experiments has a nuclear source, and if there's not commensurate amounts of nuclear energetic radiation, then that presents a theoretical paradox. That's going to be the biggest theoretical headache that we have to deal with.
Thank you.
Q value for the experiment. Q value. What's the Q value? Well, the Q value is the energy you get per reaction. So in this case, imagine starting out with two deuterons, ending up with two deuterium atoms and ending up with helium-4 atom. And the mass difference between them, so the D2 is heavier, this isn't helium-4, but if it were helium-4, the picture is still qualitatively be the same. But the mass difference between helium-4 and two deuterons is known in nuclear physics, 23.85 MeV, which is what we call 24 MeV. So if we're going to contemplate the possibility that we're starting out with two deuterons and we're making helium-4, then if you're seeing energy being produced, and if you're seeing helium-4 in the off gas, you'd like to know whether the amount of helium-4 that you see is the amount you should be seeing if it's this number per reaction to correlate with the energy. Namely, if you produce a certain amount of energy, you can divide that energy by this number to figure out how much helium-4 you should be seeing if this were the process. And that's a number that should be accessible to experiment. So this has been studied by a number of laboratories. I'm going to be reviewing a very small subset of these measurements. McCoubrey and company at SRI ran a set of tests on what's called the CASE experiment. And what had happened is Case, who sadly is no longer with us, Case had been working with palladium catalyst material. And he sorted through a very large number of catalysts, and he developed an experiment where he put the catalyst material and put deuterium in, and he would observe a fair amount of excess heat. He sent some of his gas samples out to be tested, and the lab came back to well, there's helium-4 in it. So this seemed like a very good experiment to try to do an independent confirmation of both to see if you could get the energy and to see if you could get the helium-4. So what excess heat was seen. Helium was also seen. The helium was sort of interesting. In some of the experiments with excess heat, where excess heat was produced, helium was observed, and then the helium would sort of go away. You might say, well, helium's not supposed to be going away, what's going on? And the thought was that perhaps the helium's going onto the catalyst and not being available then for the gas measurements in this case. So this is worrisome. On the other hand, here's the 5.2 number for atmospheric background, and the it's good that you're above the atmospheric background. You'd actually like to be orders of magnitude above the atmospheric background. So that's a weakness of this experiment. What was plotted here, a number of data points. Basically, you've got measurements of the Helium-4, and you've got measurements for the excess power done with the calorimetry. And these are plotted as a function of time, and plotted in terms of energy, and plotted in terms of parts per million. And so from this curve, you've got, you find that the amount of helium produced is sort of going along with the amount of energy produced. And if you plot the energy produced as a function of the amount of helium made, then you get lines that you can run through. You'd like to see 24 MeV being the slope of the line. In this case, it's 32 MeV. You say, well, what reaction do you have in 32 MeV? And there's, of course, no obvious candidate reaction to 32 MeV. Instead, the conjecture is that not all the helium is coming out. And you can see from the curves before that some of the helium levels are going down, which means it's sticking with something. So this is a little bit high, and as it turns out that in other experiments that have been done, oftentimes when you get the Q value from the amount of helium observed relative to the amount of energy, the number is a little bit higher than the 24 MeV number that you would hope for and expect. So this problem's been around for a while. The one conjecture was proposed by Mike McCoubrey after we were sitting watching the GOTC presentation with the time result. Thanks. GOTC measured the Q value associated with the individual bursts. And what he found is that the Q value, the amount of helium that was observed, was in some cases sort of what you would expect for a 24 MeV Q value. In some cases, it was 2/3 and a half. In one case, like 20% as much. So we looked at that data and said, what the heck's going on? And I said, well, what's obviously going on is not all the helium's coming out. You make it, sometimes it comes out, sometimes some of it sticks in. And Mike's conjecture was that if it's made inside the material more deeply, then it's not coming out. If it's entrapped, it's not coming out. So the conjecture then is that some of the helium-4 is retained in the cathode. And if it's retained in the cathode, then you don't measure it in the gas. And you say, well, why didn't they see it for the helium assays of palladium? And the helium assays of palladium intended to chop the palladium up and kind of throughout, whereas probably it's the surface effects. The right way to assay for helium in the cathode is to look at the outer surface inflation plots, and this was either not done or not done very often. This was data that we've talked to, or that we'll talk about again in connection with a different issue. But in this experiment, M4 experiment, there's a current ramp up here, and then SRI, they had found that a current ramp was conducive for inducing an excess heat burst to occur. So there's a current ramp, excess heat burst follows. So the excess heat burst is the blue measured values. The green values will become important in a few minutes, 15, 20 minutes, it's less important now. But the thing that draws our attention here is that M4 was done in a helium-link type cell with the mass spec next to it, ready to go. So with this amount of heat produced, you can compute how much helium-4 that you should have seen. So if you start out with this amount, here's atmospheric, here's the initial amount in the D2. If you integrate up from the energy produced during the heat burst, you would have expected to see this much helium-4 if the number were 24 MeV per reaction. So sample was taken at this point, or measurement was taken of the inventory of D2 that was available. And the number is smaller than this. It's 62% of the amount that you would hope for. 62% was sort of the kind of on the order of what you would have gotten from the case experiment, and the kind of shortfall you had in other experiments that had done helium-4 measurements. So Mike says, well, if it's hanging out inside, let's wait for it to come out. So they waited and took another measurement. A little bit more helium-4 came out at this point. So they have go from 62% to 69%. So they waited and waited and waited and waited, and at some point they thought, well, instead of passively waiting for it to come out. Let's drive it out. So they went through a combination of anodic cycling. So if you run it cathodically, you load the deuterium in. If you run it anodically, you deload the deuterium. So the thought was this maybe as the deuterium is going out, it'll sweep the helium with it. Additionally, the cathode was heated. So if you heat it up, you can get the helium to outgas. And another sample was taken, the background sample. So if you add this to the infiltratory you already have, you end up with a number very close to 24 MeV. So the result of this experiment is that this was the very first attempt that somebody had made to try to scrub all of the helium-4 out of the cathode going excess heat first. The amount of helium-4 gone after this procedure is very close to what you would have expected from the energy produced if the reaction value, the Q value, was 23.8 MeV. And although the uncertainty is, there's some error bars associated with the midpoint value here that corresponds to the measurement is very close to the expected. So let me pause for comments or questions so far. Yeah.
Sounds like an intake and out, an exhaust stroke. You just taking materials and reacting, you're sending these all down. That's what it sounds like.
Well, that's the basic picture. You start with D2 as your fuel. You interact with it in some new way that has not been seen before. You get helium-4 coming out as your product. And the energy per reaction seems to be consistent with the mass difference energy, which you would expect to be associated with it if that were the mechanism for D2 somehow going to helium-4 to you heat out. So that seems to be consistent with this experiment. Now what you'd like to have like a dozen of these experiments done even to higher precision for the energy and for the helium-4. Sadly, within the field, based on the headaches associated with getting resources in the field, there's exactly one other measurement that's been done, and that was done at India Fiscati. This is perhaps hard to see and hard to follow, unfortunately. The place to start is there's something that says background here, and I think there's the line right about here, which is the atmospheric background level. And you have 3 experiments where excess heat was observed and helium measurements were done. So you have a data point here where you've got 23.5 kilojoules of energy was measured during excess heat burst. You've got a helium-4 measurement of this number of helium-4 atoms. This is well above the atmospheric level. I'm sorry, this is what you would expect if you collected all the helium. This is the value that's measured. So it's above the atmospheric background, but you're getting about half as to what you would need in order to support it. But in this case, there was no effort made to scrub out the helium-4. The same kind of thing here. 30 kilojoules, this is how much helium you were hoping for. This is what's measured. Doing a little bit better. This is close to the 60% number, sort of like what was seen in SRI and the N4 experiment. In this experiment, here's what it is, much less amount of energy, was only 3.4 kilojoules. But on the other hand, in this case, an effort was made to scrub out all the helium-4. And in this case, the measurement and the expectation are within like 10% or so of one another, but sadly, they're not very far above the background level. So this is the second data point we have for an experiment where the helium-4 was observed in connection with the heat and some scrubbing. So,
what's the volume of helium-4 to D2 in the experiment and post-experiment? Is it 1%, a millionth of a percent? I'm just curious.
Percent of what?
Volume or atoms?
Well, if you like, the atmospheric background is 5.2 parts per million in air. So 5.2 parts per million. Here's the 5.2 parts per million. Well, this is a very relatively small amount of helium for this experiment. But again, the energy is not all that large. If you put in a Mitchell nanner into a cell, helium lake tight, let the thing run and produce a few megajoules or something. Yeah.
Did Alpha Cell use heat or anodic current or both?
I don't actually know. I know that they made an effort to there's not much documentation as to how this done. Okay, so now we're gonna shift gears a little bit. So far we've got to the conclusion Helium-4 looks from experiment to be the product of whatever new reaction is going on. We're interested in building up a theoretical picture for what's happening. And as I mentioned before, parameter space for theories are like infinitely large. And if you're a theorist, you could like point anywhere in this large parameter space and you could be arbitrarily wrong. And so if you're gonna maximize your chances of getting a theory that's remotely relevant to reality, you need to have experiment inform you and settle as many theoretical questions as possible. So this is going to draw our attention to another issue. The other issue has to do with the following argument that if helium-4 now is the product of the reaction, that's some information we didn't have before. Normally in nuclear physics, if you're doing nuclear reaction, you've got products coming out. You can put detectors, you can measure energy distribution or angular distribution, dependence on energy. You can measure things to depth. You can learn pretty much everything there is to know about the experiment from watching products come up. Now, in this particular case, we have a product, and if we put on a nuclear physics hat, the very first question we'd be interested in is, if it gets made, you're making energy, then the normal nuclear physics picture is that it should be coming out with some energy. So we'd like to know what that energy is and measure it. So that's the next step in a very long and tortured argument. Okay, so that's where we're headed, and I guess we've got a stop or two along the way. I guess before getting there, having helium as a product has a big impact on basically your experiments and moving forward to a technology to produce excess heat. And that brings us to the temperature effect that was first observed by Fleischmann. So the basic idea is that if you run these things at higher temperature, they work better. And I'm going to argue that this is as a result of the helium, getting rid of the helium. So Fleischmann and Pons and ICCF3 popped up and said they had a new protocol that made use of feedback. And it was very successful. They would start out running at low current density, they ramp the current density up. So at low temperature, you can load more easily. High temperature loading is problematic. So you load at lower temperature, and there's, I'm going to guess that there was loading that occurred long before T equals 0 here. So then they ran it at relatively low current, and they cranked the current up and started running at high temperature. And then they let the temperature increase. And by saying let the temperature increase, the power produced by the reactions is what's responsible for increasing the temperature. They didn't add power to make the temperature increase. And this was their protocol that was incredibly successful. Other people didn't do much following up on it, even subsequently, which is sad. This was a major step forward. And what was interesting is that, as you'll notice, there's these little calibration pulses that they use in the data. So Fleischmann and Pons would recalibrate their system again, 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 again. They were a little bit like Mitchell in terms of wanting to have calibrations just like every so often. What they noticed in their calibration data was an interesting effect. So here's before here's a calibration pulse before an excess power event. So there's a cell potential and there's a cell temperature. Our attention is drawn to the cell temperature. So the cell temperature is coming down. You can almost draw a line here. So if you hadn't had a calibration pulse, the temperature would continue to drift down and it would go something like this. Similarly, after the excess power, the temperature comes down. Looking here, it looks like the temperature is coming up actually, so maybe I've got the wrong curve. It's got to be this one. But I have to say it's looking like this one. Anyway, let me give it to myself as a homework problem to stare this data more at my leisure. But Fleisch and Pons put in the dotted lines in order to guide your eye. So basically, the system goes back to the same temperature that it had before the pulse, following the trace of it. But during the excess power, when you put in the calibration pulse, the relaxation temperature is to a level higher than would have been expected to have the calibration pulse not hit. So what's going on here is that when excess power is occurring, if you put in a calibration pulse, you increase the level of the excess power. So what's going on here is Fleisch and Pons are not only doing their calibration pulses often because they want to make sure their system's calibrated, but they're putting it in often, and each time they put it in, it's incrementing the temperature, and the system seems to work better at higher temperatures. So there's a non-linearity in the response to excess power with respect to temperature. So this was observed by others. Here's some data from Dennis Craven's temperature, calibration pulse, and then temperature after the calibration pulse. So this is a calibration pulse at a time when excess power is being produced, and the calibration pulse has raised the level of excess power. In this case, you can see it is raising the level of the temperature. So this is interesting. So this was the first observation of it that was made public of this temperature effect. It was measured in 1993 by Ed Storms, who had a cell running and then changed the temperature and measured excess power. And the function 1/T log excess power fit it to this particular form. You got the delta E of 673 millivolts. Similar measurements were done by Mitchell, and Les Case also found that the excess power in his experiment depended on the temperature, and he reported a similar scaling of excess power with respect to temperature. Let me plot out e to the minus delta over KT for you if there's any questions to how big of an effect this is. So, here's from temperature. Here's 400 Kelvin or 100 C, or so boiling point of water is 100 C, so 273 is up here. So you're getting like a factor of 100 increase following this particular exponential law in the level of excess power between room temperature and the boiling point of water. So that kind of factor is a big factor. So the Fleisch and Pons power run up and have the cell operate at higher and higher temperature. It work much better for this kind of reason. So takeaway message, let me pause and catch my breath. Thoughts or comments so far? Okay, so power goes up, seems to depend on temperature, and it depends on temperature this way. And that suggests that there's a delta E barrier energy that's showing up in the problem. Initial question is, what might be the origin of this delta E? Now, when this was found, people in the literature made all kinds of arguments that, well, this is the barrier energy associated with the fusion reaction. So two deuterons coming together, so 0.7 electron volt barrier being forced helium-4 being able to come together and fuse. Of course, the physicists would cringe when they hear arguments like that. So this is a chemical level of energy. It's not a nuclear level of energy. So there's, in my view, there's no way it could be associated with the Coulomb barrier, the nuclear part of the problem. So the argument is perhaps this is associated with helium diffusion. So the picture that comes to mind is that we argued yesterday that we want to make a monovacancy to get the electron density to be lower so we can make D2 form. So suppose that all of this is right and the D2 turns into helium-4, either at the same site or some other site. You can imagine you've got all this work now to make your vacancies. If you're making all this helium-4, helium-4 would want to find these vacancies because we saw by embedded atom theory that the lower electron density is going to give you the lowest energy point. So if you make helium-4, it's going to go to the traps, which are going to be monovacancies in this material. So you make lots of helium-4, it's going to plug up your monovacancies. And your monovacancies are busy plugged up with helium. They're not busy doing what they need to do for the D2 to make you more energy. So the thought is that if you've got a system that's working reasonably well, you would expect the active sites, in this case, the monovacancies, to be filled with helium-4. And that could be the limiting, that could be what limits the rate of excess power production. Now, if that picture were true, then you might argue that getting the helium-4 out would be what it is you need to do to have the system work at a high power level. And there's two parts to it. One, you've got to get the helium-4 out of the trap, and then you have to have it diffuse away from where your vacancies are. And those are two very different processes. The one in the function Pond's experiment, the thought is that the diffusion process would be might be rate limiting, basically because that gives a number that's more closely matched to the excess power curve. So Zia et al. Did embedded atom modeling to get an estimate for the helium diffusion coefficient. And they got it in the normal form, eta minus delta over KT. And they're an estimate for the barrier associated with diffusion of helium and palladium is 720 millivolts. This number, for all practical purposes, is exactly the same 700 millivolts as is measured for excess heat as a function of temperature in the storms experiment, and it's essentially the same number that Mitchell finds, and it's essentially the same number that Lescase finds in his experiment. We can even plug in numbers to get a diffusion coefficient. This diffusion coefficient is actually quite small. Helium doesn't go very fast through palladium. So we pull them out. Here's Storm's number. Here's Zia's theoretical number. From my point of view, they're the same. You could argue that this barrier is higher because Zia was doing pure palladium and not loaded palladium. Palladium atoms are a little bit farther apart, the barriers are lower. So if you did it for palladium hydrate or deuterite, I get a number closer to here. So if anything, you're going to correct the number, probably be closer to the excess heat related number. The question is, if you take the diffusion rate, you say, well, how far do you have to diffuse before you can get out, and how long does it take? So you apply square root of d times tau as, so if you take tau here and have this get the L, this gives you a characteristic distance that you can go in a characteristic amount of time. So, for example, let's choose an hour just for a number. And at this point, roughly, you get about half the helium out. You go over here and you get something like 3 times 10 to the minus 6, 10 minus 6, 10 minus 5, 10 minus 4. You get roughly 300 angstroms. So if your helium were sourced 300 angstroms from the surface, then in an hour, you could get it out, basically half of it out by diffusion. If you have to wait 10 hours, then it's 1,000 angstroms. If it takes 100 hours, 3,000 angstrom, 1,000 hours, micron. Well, we're recalling in Gottes's experiment, the helium was pretty much commensurate in time with the excess heat burst. And the scale was in terms of hundreds of hours. So if we were to go to 100 hours, just a characteristic number, we could say from Gottes's data, in order for that good of time correlation to occur, you had to be something within, say, half a micron or less distance from the surface. Otherwise, you would not have gotten your helium. If you pursue that route, you can start to argue that, well, maybe the cases where they didn't see as much helium, maybe they were a little bit further in from the surface, and maybe it came out over a longer time or some such. Anyway, one thing that would be really interesting to do is to imagine an experiment where you've got time-resolved helium detection. You run in, you do a very short, reasonably short, maybe an hour's worth of energy production, then you turn the energy production off with a nano or something, and then watch for your helium to come out. Then, depending on how long it takes, you could get some estimates as to how far it had to go if it were going through plate. Now, of course, in the nano, the picture's a little bit different. But anyway, if you had a controllable experiment that were monolithic rather than the nanoparticles, then this would get more information.
How thin can the layer of palladium be and still get excess production? Does there have to be a depth that's sufficient for the hydrogen or deuterium to build up in order to facilitate the
This is a question of great interest currently among the community. The nanoparticles, I guess some people have asserted very strongly you have to be something like 70 angstroms or so in size for nanoparticle to begin to see excess energy.
Thank you.
But I don't know of a systematic study where people have gotten sizes and power and plotted it out on an axis. That really needs to be done on these days.
When the reactions take place in your model within the vacancies, and there's release of energy, is it your concept then that this happens kind of uniformly through the labs so that energy is released kind of over a broad volume or a fairly broad area near the surface? Or do you think there's more like a localized thing like that so-called nuclear active environment?
You're getting way the heck ahead of my talk.
Okay, I'll shut up.
The answer is the latter. It's not delocalized.
This spot?
Delocalized.
I really like your story, but there's a couple of minority reports which you've got to kill as far as, because there may be multiple things going on. For example, raising the temperature causes a desaturation of the palladium. The deuterons are going to come out. They have to go somewhere. So it could be that these calibration pulses cause the deuterons, the free density, to go up, and then they have to find a vacancy. It could be an initiating effect.
Actually, let me emphasize your point. Instead of killing it off, let me agree with you. There's a simple argument of helium diffusion and the simple exponential, having the power go exponentially is a function of temperature and being able to get this simply. This presumes that the system is otherwise unchanged, that all the D2s are remaining in place. Your argument is if you raise the temperature a lot, then the loading's going to go down unless you've done something to keep it the same, and diffusivity is going to increase so that materials can move around and stuff happens. So that's exactly right. And I thank you for bringing up that point. That I should emphasize it. You're exactly.
It's as if the calibration helps both sides. It gets the product out of the site and gets the fuel into it. And then there's two effects, which is the increased temperature can affect activation energy, let's point out. So, and it also affects the diffusivity.
So when you're giving a presentation in a class, what you try to do is you try to isolate one issue to make the world simple so your students can understand and take all of the other complicated issues. You forget about that's for homework or for reading outside of class.
Yeah, well, I think this discussion relates back to the point where I'm getting ahead of the story. You know, if the problem is plugging up sites, then you're going to have these very high temperature reactions that are going to give you the temperature you need to get it out of there.
Again, you're getting ahead of the story.
Okay,
Wait. Basically, that's sort of the next issue that we got to begin thinking about. We were sort of plodding along ridiculously slowly, but to sort of, the issues are complicated, and the idea is to take one issue at a time and chew on it until we're done chewing on it and go on to the next issue. So I apologize. You guys are racehorses here.
Tell me again what the depth from the surface is shown on that curve for 1 hour.
Okay, so for 1 hour, you go up to here, you go over here. That's 300 angstroms.
Thank you.
Okay, I want to think briefly about nanoscale palladium deuteride and helium diffusion. So I'm thinking about Mitchell's devices and other nano device experiments, because there's a lot of experimentation going on with nano nickel and nano palladium powders and nanomaterials and zeolites and so forth. So the argument that helium-4 and accumulation in active sites is going to, it's not so much poison, just it blocks them. It's you know, if you want to burn wood in your fireplace, you got to clean out, you know, the remnants of the last fire periodically, or else it's not going to work very well. So we're arguing that the temperature dependence in some experiments, and this is some, it's not all experiments. For example, at SRI, they tried looking for temperature dependence for experiments that didn't work quite as well as some of these, and they didn't see a strong dependence on temperature as was seen by Fletching, Bonds, and Swartz, and Mitchell and others. So if this is true, we might imagine that in a system that's working well, it's limited by helium diffusion, that if we could arrange for the helium to leave more efficiently and quicker, that we'd be able to clean out our monovacancies and operate more often and get a higher power density out. And so the conjecture made a long time ago is that this is the advantage for nanoscale devices. And I guess at ICCF 17, Arata and his colleagues presented a paper arguing that this exactly this very similar idea was used also for the higher power density for nano systems. So sort of in a big picture here, I'm thinking of this as being sort of a millimeter scale cathode. The active sites are near the surface, but I have to go a long ways. And a long ways might mean 1,000 angstroms. It might mean 3,000 angstroms. Whereas if I've got little tiny nanoparticles embedded in a zirconium oxide mesh or matrix or nanoparticles either by themselves or I'm not sure if they can work by themselves or with some other matrix, then if I make helium inside, if I've got a nanoparticle, all I have to do is go from where it's born and get out where it's not the particle anymore. So for example, in an insulator, the electron density in the insulator is much lower. So I know by embedded atom theory, the potentials are much lower. So helium can diffuse through insulators really, really well. So that's the basic picture. So Mitchell's got these astronomical numbers for power density. And I'm going to argue that so on the table of conjecture that the size of the nanoparticle is connected to the power density. So imagine a world when Mitchell dials in the nanors. He's got 200 angstrom nanomaterial, 150 angstrom, 100 angstrom, 70 angstrom, runs them all. And if somehow everything else can be made identical, which is probably the biggest if in the world, then the power level operating at constant temperature plotted as a function of size. If this idea is right, then the smaller scale nanoparticles would operate at a higher power density. That's to be tested. So I'm patient, Mitchell. You can send me the data tonight. I'll stay around. Okay. So Fleisch-and-Pons experiment, your generic Fleisch-and-Pons experiment, slow diffusion, quote unquote long helium diffusion path, maybe 3,000 angstroms, maybe 1,000 angstroms. Fleisch-and-Pons experiment near the boiling point, much faster diffusion, but probably same long helium diffusion path. So this works better than this. Nano near room temperature, very, very high excess power, but the diffusion is slow, and high diffusion is not limiting here. Actually, probably it's the escape from the trap that's going to be limited. So these are other curves where, and the discussion earlier was going to limit that the diffusion was limited, but we begin to get some evidence in the recent 2 laser experiments and the data that for the ones that work really well, that we're getting a higher delta E. The statistics are too small to be sure of it, but I'm wondering whether we're actually starting to see the effect of traps, because trap will give you bigger delta E than diffusion. Nanner, higher temperature, well, man, higher temperature nanner should, if everything else could be held constant, density and loading and everything constant, that should give a frightening number for the watts per cubic centimeter.
Can we talk about number 2 for a second? Go back.
Sure.
Okay, here you posit the faster diffusion at higher temperature versus the activation energy. In classical electrochemistry, we see a doubling every 10 degrees C if it's activation energy, 30 degrees C more or less if it's diffusion. Do you have the numbers for that?
Again, your question's a great question. The situation's more complicated. From the to dig your way out from palladium. Okay, you're starting because the electron density is high. You're starting up. To go from here to the next one, if you don't have relaxation, is about 1.5, 1.6 volts. If you have relaxation, it's the 0.7 volts. To go from the monovacancy, so monovacancy would have, in the middle, you'd have very much lower density, so you'd be looking at 2.5 volts to get up, but if you include relaxation, maybe it's 2 volts. And then in Letz's experiment, we're seeing delta E's that were maybe 1.6 volts or something, corresponding to the difference in the power level of temperature. If we were assuming the conditions were constant, which may or may not be true. So those are sort of the numbers.
But if we plotted out excess power gain as a function of temperature.
The more interesting numbers, the power per cubic centimeter of nanomaterial stuff. That's the thing we should plot to do this studies.
So if I could try to simplify it for myself and maybe some others who don't have a physics background, the engineering problem would be to, other than freeing the traps, is diffusing out the helium-4 and not diffusing out the D at the same time.
Again, a great question, but let me take a step back. So you got to get your helium in your vacancy. You got to get out of the vacancy. So that's hard. That takes a long time. And once you get out of the vacancy, it can fall into another one, which means you haven't done anything. Or you can diffuse away and get it the heck away from your vacancies, period. Now, in the Fleisch-and-Pons experiment, it's taking a long time to get out of this vacancy, but presumably there's a lot of them around. So in that case, the important number is how long does it take to get your helium away from everything and out into the gas. So under those conditions, the thought is that maybe it's diffusion limited. But then once you make the thing a small scale and have a shorter path length, then the diffusion's not going to matter anymore. It's going to be the trap, because once you're out of the trap, then you diffuse a small number of sites, and then you're free. You're in the air.
And if the D2 takes up the trap, then the helium-4 will bypass. It'll just be gone, right?
It's a good question. I kind of doubt it. I mean, if you've got your octahedral sites occupied, you still got plenty of room for helium in the middle of the cell. So it's not quite as simple as that.
So again, this might just be not make sense, but so as you're fusing out the helium, you get it out of the trap at, there are vacancies. Is there a way to load or create a flux into these materials that's directional, where you can be bringing in the D2 from one side and fusing out the other, so the helium-4 and D2 is coming out one side, but you're only replacing the other side with an influx of D2, and that way it's kind of a flush. Or
That would be called diffuser. That's what Mitchell's device does operationally. I hadn't been thinking of it in those terms, but you know, certainly if you arrange a flux, you could sweep out the helium, and that would help remove it if that's what the limitation was. In the NANR, I don't think it would make any difference because I think the time getting out of the trap is going to dominate things. But in a fuser and Fleisch-Pons type experiment, but more extended active region, having a flux would very likely be pretty effective in helping get the helium to be calculated out and double checked and so forth. But it sounds like a way that's interesting. Okay, takeaway this probably. We had plenty of discussion. We will move on. Okay, so we're now ready for another step. And the next step is to say, if I were putting on my nuclear physics hat and say, aha, you have a reaction that's a nuclear reaction, you're making helium-4 as a product. What's the kinetic energy that it starts out with? So at the microscopic scale, I want to begin thinking about what's going on at the microscopic scale. And having helium-4 identified as a product naturally now aims me in the direction of trying to ask questions about what's going on at the microscopic scale. And that leads us to pull out the old physics books and see what this New Zealander Rutherford had to say about it. And so back in the days when nuclear physics was yet young, they found radioactive material produce alpha particles. And in a plastic experiment, they found that alpha particle hitting a gold foil would give rise to many tracks that would stream straight through, so you have these soft glancing angle collisions. But every once in a while you get a wide angle collision. And this is really interesting because at a wide angle collision, it means basically you have something that's sort of small hitting something else that's small, which sort of leads you to imagine nuclei have the same as billiard balls. Rutherford, of course, is famous for the billiard ball picture of how nuclei works. So nucleus incoming, scattering off of another nucleus with bangs, it hits it. And it's sort of the same kind of effect that's happening with billiard balls hitting one another on a billiard table. And this is nice because what it tells you is that it tells you that you can make really interesting predictions about what happens during the collision process on conservation of energy and conservation of momentum, which is sort of what dictates how billiard balls do these things. So the idea is that you have one billiard ball coming hit the other billiard ball. The momentum before the interaction has to be the same as the momentum after the reaction. The energy before has to be the same as the energy afterwards, unless you have a reaction that produces or takes up some energy, in which case your energy balance might be a little bit different. But these two constraints together go a long ways towards constraining what happens during a fusion reaction or during a nuclear collision process. So this simple billiard ball picture, the argument here, the advertisement here, is incredibly important. It gives us a lot of intuition and can be used as a computational aid. For example, suppose we have two neutrons coming in, we've got helium-3 and a neutron coming out. So we've got a normal conventional D2 reaction. Then we can think of initial state, we can think of final state, and we can, under the conditions where the initial state is a molecule, so we have tunneling, so we have no initial velocity, we can figure out what the final velocities, final energy is going to be. And using conservation of momentum and energy at the same time, we conclude that the neutron in this case has got 3/4 of the reaction energy, and the helium-3 has got 1/4 of the reaction energy. Or alternatively, the 3 + 1 final state is 3:1 inverse to the masses to the final state energies. So if you look at the reaction energies for the DD reaction processes. In fact, you find 3 to 1. You find 3 MeV proton and 1 MeV triton, roughly. So the simple billiard ball picture with almost nothing else is giving us an astonishing degree of predictive capability for nuclear reaction products. And that's important because then if you've got a cold fusion reaction, which is something new nobody's ever seen before, and if you believe helium-4 comes out as a product, then you can use Rutherford billiard ball dynamics to go ahead and analyze things. For example, if you could measure the energy of the helium-4, and if you believe that the reaction energy is 24 MeV, then if it's created by pushing off of something, you can actually tell from the measurement of the helium-4 energy what it is that pushed off it. So this argument came about, I was talking about my ideas and models at a Naval Postgraduate School. Various famous physicists were invited by to interact with us and discuss our ideas. And I finished a presentation, a couple-hour presentation, hit all the important points. We got to the end, and these famous physicists had been happy with the presentation all along. He said, well, there it is, the helium's, I was arguing at the time that helium's produced stationary, and he said, that's impossible. This is all very nice, but this is the way it has to work. The 2 deuterons have to come together next to the palladium atom. They push the palladium atom back, and the helium goes forward, and that's what's happening. The certainty with which he expressed that idea was impressive. He knew what the answer is, and I thought, if I can only learn from this person, then I would understand the world much, much better. So that got me thinking. I thought, what can I do to measure the helium-4 energy? Because we could solve the problem. We could get the answer. We could know how the reaction works. If we could get this helium-4 energy. So I was thinking, and this says, and we could learn something important about the reaction from the helium-4 energy. So not just learn about the reaction, we could settle the issues if we can measure the helium-4 energy. So I'm thinking about it, if we imagine that we got D plus D next to something big and heavy, or maybe small and light, let's not prejudge these things, then if this is the reaction, that if it's pushing off of something small and light, giving us helium-4 most of the time, then we can figure out what it's pushing off of if we get the helium-4 energy. So thinking, can I put it, at the time I had some alpha detectors. I thought I could put an alpha detector in here at the cathode. Of course, I've had that argument for a decade or more with McCoubrey. So, the base will eat your alpha detector, and then the alpha detector near the cathode loading be low. In fact, the experiment you remember seeing excess heat. So we're not so compatible with the electrochemical cell. If you CR39, people tried that. Also, that seems, I don't know if anybody has success getting excess heat in electrochemical cell CR39 next to close enough to the cathode to do an alpha measurement. Anyway, not an easy task to get the alpha. So I was sitting here stewing about this. There's got to be some way to do it. And then I had a brainstorm. And the brainstorm was, if we need a detector, why is the cathode, the deuterated palladium telluride cathode, as our detector? Because then if an alpha particle comes in and hits our detector, if it's got a lot of energy, it's going to smash up one of the deuterons and disintegrate it. We'll see a neutron coming out. If it's got less energy, it'll hit a deuteron, which will hit another deuteron, and we'll get a diffusion event. So if you think about it, palladium deuteride is actually a halfway decent nuclear detector. The only thing you're missing is a good calibration for it. So the idea is, if this works, the idea would be to take an experiment, take your cathode, take your Fleisch-Pons experiment, load it, get excess heat, put a neutron detector nearby. And from the neutron detector, you can infer from the number of neutrons that you see that correlate with the excess heat. If you calibrate the palladium deuteride detector, getting to know what the alpha energy is. So I rolled up my sleeves. There's this nice Ziegler has written these codes called, used to be trim, but the more recent versions of it are SRAM. But they've got these codes that do energy deposition calculations. So run these calculations with setting an alpha particle through palladium and palladium deuteride, one's in black and one's in blue. I'm not sure I can tell the difference at this point. They're very close to one another. You can use these codes to calculate the range. So for example, if you've got an MEV alpha particle, you've got a range in palladium deuteride of what looks like just under 2 microns. So you can calculate the distribution of the energies, the range, and the trajectory. You can start evaluating yield for different potential reactions. So in this particular case, the idea is that we've taken an alpha particle and we're going to disintegrate a deuteron. So it's going to hit a deuteron head on. The deuteron splits off, the neutron goes one way, and the proton goes the other way. And here's the reaction cross section. So what this says is that if the alpha particle's got basically 8 MeV or higher, this is the dominant process, which will give you a very large number of neutrons. You'll get, in this case, you'll get between 10 to the 5th, 10 to the 6th, maybe even higher neutrons per joule produced. So this will be a completely unambiguous diagnostic for alpha particles at 10 MeV or 8 MeV and higher. For the more subtle reaction where an alpha particle hits a deuteron, which hits another deuteron, you get diffusion, secondary fusion reactions. Turns out this is a ridiculously sensitive detection mechanism. And it can measure the alpha energy basically down to levels of 10 kilovolts or so. If you get as many as 1 neutron for every 100 joules. So if you like, we now have a calibration for our palladium deuteride alpha detector. So it's very useful, very convenient. So I thought, let's go and begin looking at experimental data. So here's data from an early experiment, reasonably early, 1993, experiment from Takahashi. Not sure if you can see it or read it. The top one is excess power. And the excess power high current protocol goes way up. This number is 100 watts, 150 watts, 50 watts. This is sort of a big high power kind of experiment. There's another curve down here, which is a low current density kind of thing. And Takahashi invented a high-low current protocol where the cathode would be around high current density for a while, low current density for a while. The idea is that the excess heat bursts are correlated with the high current density. Now, neutron emission is correlated with low current density in other experiments. So Takahashi wanted to test to see if he got neutrons correlated with either high current or low current density. In his experiment, there was some correlation, as I recall, with low current density. But in general, there's not a particularly strong correlation between neutron emission and excess heat showing up. So neutron emission is largely uncorrelated with excess heat generation. But from this data, you can go back to say, well, how many source neutrons were there, roughly? And from this experiment, from a number of other experiments where the data was published in enough detail that you can sort these numbers out, there's basically essentially no correlation between neutron emission and excess power in all but one of the experiments. In one experiment, there was the weakest of correlations, where maybe there might have been a correlation. But the upper limit would be 1 neutron per 100 joules from the data that's been taken, so the upper limit for the center. So we can go back and we can plot the different, from these different experimental data, we can get the upper limit for numbers of neutrons per joule. And from these lines, we can determine what the upper limit for the energy of the alpha when it's born. And that number is certainly less than 20 kilovolts. There are 3 different curves of different assumptions for the screening going on palladium deuteride. The blue curve is probably the one that's closest to reality. So the answer is if we're making 24 MeV worth of energy, not very much of that energy is going into the kinetic energy in the alpha. That's a unexpected, a very big and important result. It says that the alpha, as a product, Helium-4 is a product, Helium-4 nucleus is called an alpha particle by the nuclear physicists. The alpha is basically born nearly stationary. We can go back now and we can use that number to try to sort out what the reaction mechanism is. If we had two deuterons interacting, coming together to form an alpha near palladium nucleus, the Helium-4 would have 23 MeV. That 23 MeV, we would see the breakup reactions. We get a very large number of neutrons. That doesn't happen, so no, this doesn't happen. If it happened next to another deuteron, we would get basically 8 MeV alpha, which we would know from the deuteron breakup reaction. If it was pushing off an electron, we would get 76 keV Helium-4. And that's inconsistent with the experiment. Plus, we would get a 24 MeV electron, which would be easy to see. So the bottom line is that we can rule out all Rutherford picture reactions that form D plus D pushing off of another body to make Helium-4. It's just simply inconsistent with the data by orders of magnitude. We can actually go a step further and we can pretty much rule out all plausible Rutherford reaction mechanisms sort of by the sweep of a hand based on this interpretation of the absence of neutrons with respect to excess energy. If there was if the Helium-4 is being born with any significant amount of energy, we would be seeing alphas, or seeing neutrons coming in, and we're not seeing neutrons coming out. So we know that the alpha particle is slow, less than 20 keV worth of energy. In terms of plausible Rutherford reactions, John Kim was arguing once that what happens is two deuterons come together and they interact with the nearest 25,000 deuterons, which then leave a very small amount of energy. So that's that would be a plausible Rutherford picture. Well, not so plausible, but that would be the kind of Rutherford picture reaction you need to be consistent with these measurements. Let me pause and catch my breath and entertain questions. Comments, thoughts, or questions? Are you supposed to be saying, ooh, ah, I'm supposed to be impressed. I
was thinking, could loaded palladium also by itself be used as a detect? I lost my train of thought. How long does it stay loaded? If you pull it out of if it's loaded, you pull it and then you cut off power. How long does it stay loaded? Because quickly can it be used as a detector?
It depends on how strong loaded it is. If you load it to the miscibility gap, Mike tells me we can pull it out. It'll hang around and keep that loading for weeks. And it takes a long time for it to lose its loading. If he loads it up above 0.9, you remember the chemical potential curve is way up, and the deuterium really doesn't want to be in there. Apparently, when they turn the current density off, it deloads like immediately within seconds.
Exothermically?
Yeah.
So let me be sure I didn't miss any when you're, I think you kind of debunked the applicability of Rutherford, okay? And that solves that problem that you started with. But did you also then turn around and use palladium, deuterated palladium as a detector? I mean, is there actually an instrument or a way to do that? Or did I miss the point?
I think it's happening at the same time.
Okay, so it turns out that the nuclear physicists have at their disposal a wide range of detectors that have been very successful over the years. So no nuclear physicist would want to use palladium deuteride as a detector. In our particular case, we would actually love to use one of the standard off-the-shelf nuclear detectors for this measurement. The only problem is that there aren't any available that we could take and put next to close enough to the cathode to get a measurement that wouldn't interfere with the loading and the excess heat process. So as a result, we're stuck. We have to be very inventive about what to use for detector. the observation here is that we can make use of the palladium deuteride as a detector, perfectly good detector. In fact, as we see, it's a ridiculously sensitive detector. And if, as long as we're able to calibrate it, then we can figure out what the signals internal are.
But it hasn't been done yet because of lack of availability of the instrument resources.
I don't understand what you mean hasn't been done. When the experiments have been done, people have run cells, they've loaded deuterium and palladium, they've measured excess heat, and they've done neutron measurements. And I've made use of publishing neutron measurements during excess heat bursts to develop these limits. So we now, based on a relatively small number of measurements, we now know an answer. We know that there's not very many neutrons there. And because there's not very many neutrons there, we know that in these experiments, we presume that the helium-4 was present in the experiment, although in these experiments the helium-4 wasn't measured. But if the helium-4 is present and produced as we believe it is, then we know that it was born not going very fast, with very low kinetic energy.
I think you're talking about using it as a detector at the same time as it's using it being reacting.
And that's key.
And you can measure the neutrons, say with CR32.
Well, they use a variety of fancier neutron detectors. CR39 is not a sufficient neutron detector.
So given that it's born this way, isn't it, well, where's the energy going?
You know, that's the providing the perfect question for where we're going to go next.
That's called a safe light.
There you go.
So whatever is going on doesn't work the same way as what's in the textbooks. We want to take the next step. And the next step involves my friends Calvin and Hobbs scratching their heads thinking about, we got 24 MeV. Normally in a nuclear reaction, the 24 MeV comes out in energetic nuclear products. Here, it's not, which makes this unlike any nuclear reaction that's been studied in the labs and been written about in textbooks from the nuclear physics literature. So we're basically looking at a unicorn. We're looking at something behaving in a way that we're not expecting it to behave. And the important question from this is the energy is not going into kinetic degrees of freedom here. Where the heck is it going? So that's the question that our focus is turning on next, namely that, of course, the argument we've been stumbling along dealing with one issue, another issue. Now, based on this argument here, we've got stationary helium-4, which isn't behaving like anything that we've seen before in terms of reaction. It's not got the energy as kinetic energy. So the mass difference energy, which is presumably ultimately coming out as thermal energy, it's got to go somewhere before it thermalizes. The question is, where the heck does it go? And that's what our attention is drawn to.
Last year, or possibly it was the year before, during IAP, this Diffusion week, you talked about how it might be possible this was one of your mathematical experiments that led to all these tombstones in the backyard. And you suggested that this 24 MeV was actually showing up as thermal energy distributed over a large number of sites.
Well, if you like, from experiment, we know that whatever energy is being produced is being measured as thermal energy. But I don't believe there's any possibility at all that you can go from a large nuclear quantum and exchange that directly for thermal energy.
Even though you discussed that.
I discussed something subtly different, and I'll be talking about it shortly.
I'll hush up and put my ears on.
Look for subtleties.
If you like, you can draw a simple cartoon that captures the heart of the argument. So we're talking now about D plus D going to helium-4. We got 24 MeV. And if we're talking about nuclear degrees of freedom, if it's in isolation, you can get a gamma. If it's not in isolation, it can be perhaps the energy is finding some way to go directly into solid state degrees of freedom. And let me emphasize that soon here to you go this way, but there's theoretical issues with respect to taking a large 24 MeV quantum and having it go into quanta that are little tiny itty bitty millivolt or volt sized quanta. So if you want to go this route, which sadly experiment at the moment is directing us down this route. So we would like not to go that way. We look at this with nothing less than utter horror with the possibility of having to go this way. But that's the direction that Mother Nature seems to be in.
Would a good compromise be of loaded palladium with gamma? Then you can say
Ahead of my story. The paper involved highly loaded deuterite in deuterium gas pressure in a chamber, and had a downwind on a Russian accelerator that was producing gammas and shining into the palladium deuterite, and not quite a massive production. I read this and I thought, whoa,
it's unexpected.
The nuclear folks are not going to be happy about this this experiment as well. I'll likely talk further about that experiment tomorrow briefly, because I think it's a very important experiment, and I think it's teaching us something about some of the ideas we'll be talking about today. Okay, so we're contemplating going this way. It's basically, from a theoretical point of view, being dreaming. We're not happy at all. So thinking. I'm interested in where the energy goes. Normally we get energetic reaction, nuclear reaction products, but not so here. Open up the textbooks tell me I'm nuts, and even thinking that there might be something else possible. So we got to go back to experiment the decider of these things. And it turns out it's the cold fusion business. There's basically only one which in part sheds light on this. This is the two laser experiment, and that's what I'd like to turn my attention to next. So back years ago, around 2000, a little bit after 2000, let's induce an excess heat effect coming and shining with a laser. I think the initial work was published in a paper by Bacchus, which once was a co-author of the initial suggestion, these kinds of things. So basically, the conception here is to take the cell, crank it down so it goes below threshold for producing exit heat. So turn the electrochemical current down a little bit, turn the temperature down, whatever it is that you want to do, turn it down so it's not working very well. And then shine in a laser and see if you can trigger an excess heat event by shining on the laser. So here's some data from this paper where here's the temperature. A weak laser is turned on, and you get a temperature increase. So the cool thing about these experiments is that the early experiments were done with on the order of a milliwatt laser, and the amount of excess heat that would be produced might be 100 milliwatts or might be 300 milliwatts. So it's a big enhancement of the thermal enhancement for a relatively small amount of laser power coming in. So here's an example from experiments that we've done at SRI. This is complicated, and I'm not going to try to explain the whole thing, but let me draw your attention to the issue that no laser here, but this is the temperature change, and the temperature causes a scanning of the laser wavelength. So, for example, here, the laser is turned on and it's scanning its wavelength. There's an excess heat response that changes while the laser wavelength is scanned. And then when the laser is turned off, the excess heat turns off. So, if you like, this is a demonstration control. We can turn the excess power on, we can turn the excess power off. That's imperfect, and there's issues, and it takes longer to turn off here and there and so forth. But that's what I'm hoping to see in this data. So we have the ability to trigger an excess heat event with a laser. And in this particular case, the excess heat persists more or less as long as the laser's on. And when the laser turns off, the excess heat goes away. When we saw this, when this experiment was introduced to us, we were astonished by it because this was an unexpected result. And the immediate response I had was, great, very responsive one laser. What about two lasers? So Dennis looks and says, why two lasers? Why would anybody in their right mind put two lasers? He says, he must be a theorist. And I thought, well, in quantum optics, people will come and they'll shine two lasers on to see if there's a response of the difference frequency of the laser. So the idea is that my modeling and my calculations and stuff, I was thinking optical phonons, that's a candidate for where the energy might be going. The optical phonons are 10 to 20 terahertz, and it's really hard to get a 10 to 20 terahertz source in. And if you had a 10 to 20 terahertz source, it's not going to go through the water. So if you could have the two lasers coming in, which can go through the water, you could beat them, have them be a different. Maybe you could learn something about where the energy is going. That was the whole point of this experiment. So Dennis, bless his heart, went to the lab, got two lasers. But before he did this, he said, well, you know, you wily theorists, you want us to do these measurements, but you have to make a prediction. So I'm not going to do the experiment until I make a prediction. I said, well, he says, what frequency difference? I said, well, the gamma point and the L point, so gamma point's around 9 terahertz, the L point's around 15.5, 16 terahertz or so. And those are the places I, you know, so he wrote it down in front of me. He doesn't know what he's right here signing this. So what happened in these experiments, the beams to overlap, and both lasers repeat polarization. So the laser is turned on. It says power burst. Apparently there's a change in the cell voltage registered in its calorimeters as an artifact. It's sort of a reproducible artifact. Other people have seen this as well. But you turn the lasers on, it turns on the excess heat. There's the excess heat at the sun. And he was happy. And I was happy. I was thrilled. And so he scanned the frequency difference, and here's what you get when you scan the frequency difference. You get a sweet spot, and you get a sweet spot in this experiment around 8.1 terahertz. And you get another sweet spot around 15 or so terahertz. So these two correspond to the ones that have been suggested, and then you've written down in the notebook. I'm going to ignore the third one. The third one, we've not sorted out what the third one is. I think the leading conjecture as to what it is that Dennis has got some hydrogen contamination in his deuterium. So, for example, his electrolyte at the level of 1 to 2%. That would mean something in the neighborhood of 10% or higher contamination in the cathode. And contamination at that level would give you vibrational resonance, L-point-like vibrational resonance at this frequency. So that's my leading guess as to what it is, but we don't have a proof that that's what it is. I mean, the way to do it is to repeat the experiment under conditions where H is excluded from the experiment, and if this goes away, then that would explain it. Anyway, here's the gamma point, here's the L point. The reasons why these were of interest is that they're compressional. They're points where you have a compressional optical phonon mode with zero group velocity. The slope is flat. So that means that if you put the energy into these modes locally, the energy stays there. Whereas if you're here, there's a finite group velocity. So if you're here, you put the energy in, and the energy wanders off. And it wanders off very fast. So this point are special because at these points the energy doesn't wander off. And that's why they were of interest theoretically all those years ago. If you have hydrogen contamination, I did 12.5%. I did an ordered lattice, which would not be expected here, but this makes it simple so I can do the calculation. I get a resonance up here. It's not quite at the 21 terahertz that Dennis sees, but it's up there. Okay, so the reason that the two laser experiments are important, relevant to our discussion of where the energy goes, has to do with the interpretation. So the idea is that if you have a one laser experiment, the light's going in and it's hitting a plasmon resonance, mainly not so much resonance, but so Dennis's experiments coats gold on the surface, so there's thin gold globules on the surface that are nanoscale. The light comes in, these gold nanoglobules have plasmon resonance that's broad near 2 volts. I think the laser's coupling to those initially. So in the one laser experiment, your initial stimulation is up at 2 volts, and the lifetime of the excitation is exceedingly short. So when the laser turns off, the excitation is not continued. If that's what's stimulating the excess heat to go on, it's not continued. And the excess heat, if it were pumping its energy in there, the decay time's so fast you can't have any persist. What Dennis found in the 2 laser experiment is that the excess power is very stable after initiating. And then when he turned the lasers off, the excess power would continue to remain. In the first round of experiments, it continued for roughly 2 weeks. And Swartz says, well, Peter, what do I do to get the excess heat off? So Dennis is in Texas. So I said, well, Dennis, do you have a gun? Yeah. So, but he decided not to turn the excess heat off with the fire on, which is probably a good idea. So he shut the thing down and started to do some other experiments. So the issue is that the one laser experiment, the laser turns off, the excess heat turns off. In the 2 laser experiment, when the laser turns off, the excess heat persists. So scratching it, why should that be? So I used to work on lasers. And in lasers, basically, if you've got a population diversion, which is what you need to make a laser work, and then you give it some light, then you can start drawing down the population. If you're in a cavity, the light will go back and forth and continue to be amplified and won't turn on. So you start by giving it some optical signal. You draw the energy into the optical signal, which feeds back and sustains it. So I was thinking, maybe that's what's going on here. Coming off the 2 lasers, the 2 lasers at the beat frequencies provided some initial stimulation of an optical phonon mode, gamma point, L point, maybe the higher ones, the hydrogen contamination L point. So you're putting the energy in, it's vibrating. Now the models I was looking at the time said, well, if the vibration mode's going, that's what it takes, if everything else is right, to turn on the process to get the energy to feed the reactions to happen. And in my models, the energy would go into this vibrational mode. So the conjecture here is that that the two lasers provide excitation, turns the process on. When you turn the two lasers off, the process stays on. The thought is the process stays on because some of the nuclear energy is going back into the vibrational mode, sustaining it to keep it to be on. So my interpretation of this experiment is that it provides indirect evidence. This is not direct evidence that the energy is going into the vibrational modes. It's a conjecture that suggests that the experiment's interpreted as providing indirect evidence that this is going on. Explained all that to my friend Lance. Lance says, the theorists, you take these strange positions, one foot leaning this way and the litany of warranties. He says, what the heck experiment do I have to do to have it be direct evidence that works? Heck with this indirect evidence. So what you need to do is you need to do a Raman experiment. So he said, oh, what's a Raman experiment? He said, well, you come in and you bounce some light off of it, you do a Raman measurement. When you bounce the light, you have the ability to either absorb or emit 1 phonon's worth of energy. And normally, it's a very weak effect. You get side bands, one side in the case of metal, and it's broadened out. I know this from the literature. There's one person that some years ago did such an experiment and saw the Raman side bands from palladium hydride. So we know they're there and we know that they can be seen. Now, if they're vibrating, the probability of a Raman transition should increase by orders of magnitude. The Raman side bands should go way the heck up. Now, if the two laser experiment were done with the Raman diagnostic on, and if the Raman side bands went up, then from my point of view, we would have direct evidence that the nuclear energies come into the vibrational modes. We would be okay. Let me pause for a moment. Up to questions or comments? Okay.
So the and become vibrational.
So, you know, we're still trying to focus on the experiment. The experiment is sort of suggesting that energy maybe is going into the vibrations. From the experiment, we're not really sure, except maybe localized to where the vacancies are. Of course, I've done lots of models, which I'll be talking about more later today and tomorrow, where you know, give arguments. In the models, the energy is delocalized. So, I mean, in the two laser experiment, the vibration modes would be delocalized to be hugging very close to where the vacancies are. So it'd be hanging very close near the surface.
So what were the frequencies of the two laser ones in the terahertz range? Or what were you like?
No, both were red lasers. So they were just, one was more of the laser emission change. Experiment that directs us where to go. Now, again, if you got your theorist hat on, when you're making any theoretical statements without looking at every single bit of you can get your hands on to tell you either that you're in the right direction or what's on the table as a conjecture from this experiment, and it was actually a conjecture before this experiment was done. This conjecture, at least on my part, possibly even earlier if you count the 1989 stuff. The question is, what's on the discussion is, what's on the table for discussion is, you put in vibrations. Once you have all the vacancy, you go. In order to kick it off and make it happen, you got to get things fired. is can we get some confirmation of this? Are there other experiments where by vibrating something, you get it to turn on? So the question is excess heat stimulated by excitation of optical photon modes? And more generally, I mean, the two laser experiment, we think we're coupling optical photon modes because the beat frequency, the excess power sensitive to beat frequency in the optical photon modes is what's going on. But are there other experiments that would sort of could be interpreted as working the same way? So I'm interested next in the notion of a deuterium flux. So it was noticed that excess power increases with above a threshold. This is our first step. And this is data from Fleisch and Pon's paper. And what you ought to see in this, so here's excess power. I've got some negative excess power at low current density. But if I look at 0 and I look at the line above, I see that there's a threshold. There's a threshold around 2. So this is log base 10 current density. So if I draw a straight line coming down, I go to about here. And about here maybe is, I don't know, 150, 200, 150 or so milliamps per square centimeter, which this is from a 1990 paper. This is the very first data, which I'm not sure is the first. I have to go back and check the NSF thing. But this is very early data from Fleisch and Pons showing that increase of excess heat versus current above a threshold. Similar data was we talked about before from Kunimatsu in Japan. In this particular case, you go down here and I don't know, maybe 150, 200 milliamps per square centimeter magic number for excess. Here's 0.6 amps. This will correspond to about 400 milliamps per square centimeter. But this is a foil rather than a cathode. This current threshold number seems to be dependent on the geometry of the electrode and also the molality of the electrolyte. Mitchell's got very low numbers for his threshold for So if you've got electrical current density, as we described before, the Volmer process puts deuterium on the surface. The deuterium can diffuse in and connect it with the electrochemical current. You expect a deuterium diffusion flux at the surface. So when I look at the electrochemical current in these experiments, I see deuterium flux. So we have an argument so far based on what we've seen in this data and other data that excess power responds to electrochemical current density. Electrochemical current density means flux. So this data tells me that the excess heat is responding to the flux. And that's related to optical phonons, because if you think about it, the deuterium is going to go from site to site to site in order to have there be a flux. By doing so, it bangs around its other deuterons and it excites optical phonon modes. So deuterium flux in palladium means that you're exciting optical phonon excitation. You're putting energy into the optical phonon modes. So I look at this and I see this as maybe this is like the two laser experiments. The two laser experiments is very elegantly putting excitation into modes, into specific optical phonon modes at specific frequencies that we normally understand. This is a very much cruder. You're having the deuterium atoms move site to site to site. It's very random, it's very chaotic. It's a very wide scatter, broad. So the relaxation time associated with this would be very short because you've not got one nice mode that's all organized. In this case, you're putting into mode that's working this way at one time, working this way at another time, this way at another time. So the lifetime is very short. So under these conditions, I wouldn't expect the excess heat to persist without the deuterium current running a thing in. The excess heat is sort of being stimulated by the current. So this is mode A operation. There's There's also mode B operation, which I didn't bring data for, where you turn the thing on and it goes on and it doesn't care about the current density anymore. That mode B operation would be very close to conception of like having a 2 laser experiment in Lance's lab where it gets the gamma point mode's excited, it turns the lasers off and stay and keep on going. I don't know if Mitchell will talk about that.
We showed it today.
Oh, okay, so the mode B, Mitchell showed me some data. And so Mitchell, looks like you turn the thing on and it just stays on, doesn't care about your electrical current anymore. It seems I said, that sounds like mode B operation. And for me, that was very exciting because that provides another connection between Mitchell's experiment and the Fleischer-Ponce board Fleischer-Ponce experiment. Okay. At SRI, an experiment was done which was, in my view, important and very much related to this. So in this experiment, it's the M4 experiment, which is the same one we talked about for the Helium-4 measurement earlier. So here's the current density. Current density comes on. There's a current ramp to get some excess heat stimulated. This one is the loading. So here's the loading, 0.86, 0.87, 0.88. The loading's going up, going down. So loading's high enough to be able to see excess heat if it had reached 0.95 earlier, which it had. And so the current density is ramped up to stimulate an excess heat burst. So here an excess heat burst gets stimulated. Now the excess heat goes down. Now there's no change in the current density and excess heat comes back up. So that's right, they didn't do anything to stimulate this heat burst. And I was looking at this curve and noticing that the curve that's the loading curve was busy going up and down and having all this stuff. And then when it stopped doing that, the excess heat went away. And so, what's going on? What's this mean? He says, well, what happens is the cathode breathes. It undergoes its own spontaneous dynamics where it outgasses some deuterium, brings some deuterium back in, and outgasses it. So that's what this going up and down is. This is a breathing effect. And it's a pronounced breathing effect, which stops right here for whatever reason. These cathodes have a mind of their own sometimes.
How would you measure load?
It's a resistance ratio measurement. Okay, so the argument, Mike and I have been talking about that, and I've been arguing that the flux was important for associated with excess heat. And if you like, this gave us a way to test that independently. So now, here you have current density, flux due to the current density, but here you have flux due to the breathing, which is independent of the current density. So Mike said, well, let's put together a predictor. So here's looking at things up close. So here's the loading and the breathing, and here's the excess heat going up. So he said, let's have a predictor. So the predictor says, you got your linear current above the threshold current. You go quadratic in the loading above the threshold loading, call this say 0.83 or 0.85. But then let's add into the predictor something that says there has to be some flux. So d-loading d-time, which is proportional to the surface flux. So he took this as a predictor and he fitted it to his data. And so here's the data, here's the predictor. And what you get to see is that Mike's predictor that now includes flux as part of the prediction now allows him to get to make sense out of data which otherwise wasn't making any sense. So this gives us additional evidence that the excess heat response to the deuterium flux, which would be, again, consistent with the two laser experiment interpretation, the argument that if you have a flux going on, you make optical phonons, and having optical phonons would draw the energy. So this kind of picture then is consistent with that basic argument. I'm going to pause for a moment. Waiting to hear. For my part, this is amazing. It's amazing for two reasons. One, it's amazing because the match is so good. The other thing that's amazing is that Mike is an experimental.
Is there a way to theoretically or conceptually to tune the flux is to tune the flux and have to optimize the vibrational mode of the photon? So, was it just generally affecting it?
Well, in this case, this is taking some experiments that are doing interesting things and thinking about it and understanding them. So the flux here is a sort of a brute force, kind of very ugly, crude flux that the deuterium is marching through and it's shaking everything out randomly. And the two laser experiment is an elegant and subtle approach, which is tuning the vibrational modes so beautifully. If we can make, on the one hand, if we can make progress with those kinds of experiments, and we could explore that. On the other hand, mode B operation basically says you've got a high gain system, which at certain frequencies has got a lot of gain. You come in, you get some crude broadband excitation, but if the gain's high enough such that the various high gain systems win, then it goes, in this picture with self-assembly, it would go into sort of near single mode operation just naturally because like a laser, a broadband laser, you get broad excitation. You know, if it amplifies, it's going to amplify to favor whichever node has the highest gain. So I'm thinking that these systems, in as much as they work like a laser, do the same thing. So mode B operation, I would think, would lead you towards an ordered, organized vibrational excitation. And it would be fun if we had a Raman measurement diagnostic, that we'd be able to see what that vibrational mode is that's going on if it works this way.
If this concept that is true, that it's a form of type of vibration, would other forms of stimulation, such as ultrasound or something like that, also trigger this?
It's a good question. In terms of other forms, you know, I mentioned the gammas. So gammas scatter and contribute vibrational. Gammas, a flux of gamma scattering plate and deuterium contribute vibrational energy. And fast electrons coming through will contribute vibrational energy as well. So in terms of ultrasound, there are questions in my mind about what frequency. For example, low frequency conversion is much harder than higher frequency, maybe. So it's an area of interest at the moment. I don't know the answers. Energetics experiment, we argued to have the super waves, which was very rapidly driving a flux of deuterium in and out of the surface. And we argued that in some cases, some very high excess heat was seen because of this, perhaps in part because of the increased flux in and out. I mean, this flux argument doesn't matter whether it's going in or out, both ways work to provide the trigger. You can make an estimate for how much energy goes into the, how much energy is dissipated by the surface flux. So the energy per unit volume is the deuterium current density divided by charge, the deuterium density, and the Onsager diffusion coefficient. A while back, I wanted to make an estimate to see how big this was, just to see if the numbers were close. For example, if you believe you know what the deposit energy is in the two laser experiments, a very tiny, very small amount of energy. The question is, would this be a similar amount of energy? This seemed to be a much bigger amount of energy. I'm remembering numbers like milliwatts per centimeter squared, and then the volume is a much smaller distance to have. I don't remember the numbers, but I think on my papers I've quoted the number. Okay, let me pause. Comments or thoughts? We've had some discussion.
What examples in the literature are there of what appears to be like a mode B kind of reaction where power is turned off, you don't have a very short heat after death experience, but things go on for years?
No, let me distinguish between Dennis's. When Dennis turns off the lasers, the electrochemical current is still going. In the mode B experiments, you initiate mode B excess heat. You don't turn off your current density. But on the other hand, if you ramp up or down, your excess heat's almost insensitive to that when it happens.
So you still maintain current.
Yeah. Yeah, so there are some publications in mode B, so many, but I understand from some of my colleagues that it is seen routinely and regularly. There are very large number of observations in mode B operation, especially as the art improves. Also axial flux. The idea is that you got a cathode, maybe it's a wire. So you load it radially, but you drive a current axial. This is a diagram from Trelawney's paper. But this approach was first, in general, was first proposed by, the notion was first discussed by Fleischmann at ICC and Ford. Subsequently, Trelawney, Abrada, and others began implementing systems where they would have a radial electrochemical system, but then they put an axial voltage, which would drive a very large electrical current, but it would push the deuterons one way or another, which is sort of a Kahn effect kind of idea that was motivated by Fleischmann's suggestion. This gave interesting results in experiments by Trelawney, Abrada, and Godus at Rouen has been pursuing some very interesting kinds of axial current stimulation. And in all cases, the deuterium flux, in my view, is efficient in producing optical phonon excitation, which I think is the triggering mechanism in these experiments. So this actually brings us to the NANOR. So Mitchell's not driving a deuterium flux through the NANOR, probably, in the experiments. The thing seems to respond to electrical current. I'm scratching my head thinking, what's the electrical current do? So electrical current tunnels through the zirconium oxide, but it conducts through the palladium deuteride. And the resistance is going to, there's plenty of sources of resistance, but one substantial contributions the optical phonon modes. So the electrons are going to be coupling apart to the optical phonon modes. So the thinking is that in the mode A, the electrons go through, they take all the optical phonon modes, that causes things to happen, but they're disordered optical phonon modes. So the decay rates and the loss is very fast. So then when the current goes down, then it changes or does anything, then the excess heat is proportional to the excitation of the optical phonon modes. On the other hand, if you've got a system that's got really high K and works really, really well, then he sends current through, gives broadband optical excitation, but which everyone's highest ends up winning, and then get a more organized operation, and then that's much less sensitive to the excitation produced by the current. So, anyways, to be thought about, to be tested, to try and be understood. We really need some well-known diagnostics and sort of thing. Anyway, takeaway message. Takeaway message is that this notion of getting optical phonon modes to vibrate, having the energy go back into these modes, having a lifetime organization be important. These ideas seem to connect with experiment, and that at the very least suggests that if we pursue it theory-wise, we're maybe not falling off a cliff. Maybe this is the way Mother Nature wants us to go for theoretical developments. Let me pause and catch my breath. Comments or questions or thoughts so far? Okay. All right, so we're now gonna begin shifting gears one more time. So we've been going over experimental issue after experimental issue after experimental issue. In a sense, by now we probably hit most of the important ones. We haven't hit all of them. There's plenty more. There's RF emission. There are other experiments that are relevant, but at this point, we've got to begin thinking seriously about theoretical models. And so I decided to put together a few slides to encapsulate this part of the journey. We'll pick up on it tomorrow. But I wanted to sort of go through some theory arguments without having all the theory here in order to get a bird's eye view of what it looks like. So we recognized on day one that excess heat is inconsistent with condensed matter physics and nuclear physics. In a sense, what has to be coming, and what the physics folks are going to expect, they say, well, look, you don't like our condensed matter physics? Show us your condensed matter physics. Let's see how well it works. You know, we'll test it out. You don't like our nuclear physics? Show us your nuclear physics. So at some point, from a theoretical point of view, we're going to have some condensed matter physics and some nuclear physics. It's going to have to be relevant to these experiments, and it better not give different answers for everybody else's experiments. So, you know, we can get thrown out a window or something. So the excess heat is a real experimental effect. It implies that there's something really important about condensed matter physics and nuclear physics that we collectively have been missing. And at this point, we finally got to roll up our sleeves and confront this head on and try to get a handle on it. So we've been looking for experimental results, so far, trying to get guidance for what the theoretical statements are. But at this point, we've got to start rolling up our sleeves and getting serious about the problem. So I will roll up my sleeves here and get more serious about it. Okay, so the biggest theory problem, as we've remarked numerous times, has to do with the absence of commensurate nuclear radiation. If you come by as a theorist and you're looking at this, you say, what is the heart of this particular problem? This is the heart of the problem. If you don't understand this, you don't understand the theory. Now you can see I have my sleeves rolled up, so I'm getting serious now with the theoretical arguments. Saying normally we would expect commensurate energetic nuclear radiation from a billiard ball, Rutherford billiard ball model, as a consequence of conservation of energy and conservation of momentum, sort of a classical billiard ball kind of picture. Are we ready to give it conservation energy and momentum? I'm not yet. Are we ready to give up a classical picture? Maybe. We still like Rutherford. Anyway, absence of a secondary neutron emission in excess heat plus neutron measurements basically tells us that this simple billiard ball, rather billiard ball type of reaction pictures isn't going to work. That's not the picture we're looking at. We've got to work with something different. We know energy is produced in the experiments. We know it's not chemical. We know energetic nuclear radiation doesn't go into kinetic energy. We've got now indirect evidence via interpretation that's going into vibrational degree of freedom. The big question is, how could such a thing be possible? If you wander into the office of your physics colleagues at MIT or anywhere else, you're not going to join and say, well, okay, I'm going to take 24 MeV and I'm going to give it to the vibrational modes. They'll look at you and they'll call security or whatever and have you carted off to the nearest mental hospital. However, we've got experiments that seem to be saying that this is what it is we've got to think about. And if you like, we're drawn here kicking and screaming. We do not want to be drawn to this. We do not want to be having this discussion. But it's the only one that seems to be relevant to experiment. We would like to discuss anything else. We want to focus on known physics things in textbooks. But known things in textbooks don't connect with this experiment setting. So we need a way to take a big MeV quantum and fractionate it. Got to take a 24 MeV quanta to pursue what it is that Mother Nature's directing us towards to be relevant to experiment. We've got to confront this notion as a theoretical problem. We don't want to do that. I didn't want to do that back in 1989, but that seemed the only way out of this particular theoretical mess. Let me pause for a comments or thoughts.
I have a picture in my mind of what I'm understanding is, in the one situation we have a billiard ball going, a couple more and you can predict where they're going. The other picture I'm thinking in my mind is a billiard ball hitting a sandbag and distributes all the energy that way. Is that a relevant picture or not?
That would be a relevant picture for a different physical process. And one can always propose relevant, propose physical pictures and think about it. If you like, the exercise you're going through is exactly the right exercise. We would like to have a physical picture. We would like to have an interpretation. Today, I'm going to be chewing on the problem, and I'm not going to give you a physical picture today. In fact, I submitted a paper that gave a short review of the theoretical ideas, and one of the reviewer's comments was, "Oh, provide a sketch of the physical picture that corresponds to things." And get a letter from the other. "Oh, just add one. It'll be fine." I'm thinking, for a long time, I've been drawing such pictures and trying to present them. And next time I will talk about that physical picture. You're not going to like the physical picture. You're going to hate it, as I hate it. But I'm not going to give such a physical picture today. But I'm going to march in the direction of trying to get a physical picture. I really appreciate the question, and I would really love to have a slide to show it to you, the answer. But sadly, it's not going to happen like that. Question. Conversion of quantum. So the issue is if you got a 24 MeV quantum, and now that the sleeves are rolled up, we're getting serious about theory. We're talking about converting it. We've got to begin facing into the issues are. So I want to start at the beginning, and then the conversion of quanta is where the beginning's got to be. So we know it's possible to up-convert and down-convert quanta. This has been done for a lot of years. And it fits within quantum mechanics. And we understand it theoretically. We understand it experimentally. People convert up and down every day. Up-converting and down-converting theoretically are so closely related that, as far as I'm concerned, we can consider them to be the same problem conceptually. Certainly, you've got a theoretical framework to do one, it's going to do the other one naturally. It's just the way it works. And there's some examples that can get us going down the path to do this. We're familiar with up conversion. We've got laser light. In this case, from ruthenium glass laser, you've got a suitable Dublin crystal, and you phase matched and angle matched, and you match everything. Then you can get efficient conversion into double frequency. So you can change the infrared light into light that you can see. So these kinds of experiments are known. Probably you have some experience with it before. If you look at the literature, 1987 older literature, you can find papers where people will shine lasers, intense lasers on optical systems, and they'll reach highly excited levels with light that has light that's got only this much energy, for example. So in this case, 1, 2, 3, 4 photon conversion to get upstairs to people. Take spectrum, you can get high resolution spectrum. So in this case, we're converting a modest number of low energy quantum into a high energy quantum. So this is the kind of thing. The basic effect is well known. It's studied both theoretically and experimentally. In fact, there are both theoretical, there's a theoretical work and experimental work where people have seen conversion with atomic and molecular systems where some tens of photons are converted. So quite a few papers in the literature. The limit seems to be about 30 for that work. There's other work which is sort of kind of more recent, which is relevant and interesting. There's experiments that go under the heading of high harmonic generation. So the idea is you come in with an IR laser, you focus it down into a waveguide, and you go through a gas. And what happens is the light's really intense. It sort of has an electron tunnel out, it wanders off, it comes back, it recombines. The process of going this way and this way, it gets accelerated by a very strong electric field. So it has a lot of energy. So when it recombines, the radiation that's emitted is in the X-ray regime. So this is an example of up conversion, but it's not up conversion of 10 quanta or 30 quanta. in this case, it's up conversion of like 3,500 quanta photon energy kV, 3,000 quanta. Harmonic numbers 3,000. So what's going on here is there's a mechanism to take a very large number of quanta, small energy quanta, and build them up one after another, and end up with a very high frequency quantum. Not only that, but the X-rays are coming out collimated through a phased array effect. So this is an example of, you might call this an inverse fractionation or out conversion. I mean, if we were converting X-ray to large, small energy infrared quanta, then it would be the fractionation. But this is going the opposite way, which I've argued is very closely related theoretical problem. The detailed mechanisms that was proposed by Corkin, so very famous proposal, the electron tunnels out, electrons accelerated out lines. But this happens at many atoms in the same place. It goes out, comes back, out and back. And so everybody's coming back at the same time. So they all recombine to give X-rays in phase, to give the collimated beam coming up. Anyway, so we have massive up conversion. We have coherent energy exchange under conditions of reasonable amount of fractionation, in this case, inverse fractionation. So we're converting energy from some very small quanta to very big quanta. To get cold fusion to work, we've got to go from 24 MeV to sub-EV. It's basically very close to 1 billion quantas required. This is only up to 3,000. So this isn't strong enough to do it. Moreover, Corkin's mechanism couldn't work inside a palladium deuteron. But this gives you a guarantee that such a thing, at least to some degree, that's non-trivial and interesting and relevant, has been done theoretically, it's been done experimentally, and it works in the lab. Let me pause and catch my breath. All right, so for this one, you're supposed to look at it and say, ooh, and ah. Again, this is another one of these things. It's impressive what's been done. Okay, so sleeves are rolled up, back to working on the theory problem. So I'm thinking we can do coherent energy exchange by converting between quanta of different sizes. Nuclear quantums, MeV phonons are 30, 60 millivolts. So we need to down convert by magnitude in order to come up with a theory that seems to be in the direction where nature seems to be shoving us, kicking and screaming. We've got a few thousand quantum exchange. This was the basic problem that we were going to have to face to make progress. I've been thinking about this for a long time. 1989, we weren't sure if it was possible. In fact, if I had to bet back then, I would have bet against it. On the other hand, it's going to happen, and if we're going to do some theory with our sleeves rolled up, we need a mechanism to make this energy exchange work. There's no substitutes. You've got to find the mechanism. You've got to verify it. You've got to work out the math, etc.
So Peter, since you started this in '89, should your sleeves at this point be rolled all the way up to your shoulder? Sorry.
You don't know the half of it. So we'd like coherent energy exchange under conditions of fractionation. Back in '89, I wasn't the only one. Julian Schwinger, Giuliano Preparata, there were a few of us who understood that this problem had to be faced. And in this case, we can actually pose it as a problem in applied theoretical quantum mechanics. You could say, what coherent energy exchange rate is possible if you're trying to do fractionation between large quanta, small quanta. I mean, you can pose this as a problem, and it's a sensible and rational and well-defined problem, and you could start working on it. And in fact, I started working on it. Of course, the headache was I didn't know how to proceed or what model. There's nothing in the literature telling me what kind of models were going to work or what I should do or how to proceed. Based on sort of the approach that was done in my group at Livermore, when we're working on problems where nobody had the slightest notion of how to proceed or whether it could be done at all, the algorithm was proposed to solve it like this. Pick a model. It doesn't even actually matter what model. Analyze it and analyze it to death. Through the process of picking a model, analyzing it, you learn something about the model. That puts you in a position to analyze a new model. The new models could be free of whatever headaches the last one had, which means the next model will have a little bit higher probability of being one that will work. So then you go back, you repeat, you specify the new model that's better, you analyze it to death, and until it's clear whether it would or wouldn't work. Well, in this case, it's about 150 that didn't work. And this process took 13 years. Very painful and depressing experience. So there's an algorithm to solve this kind of problem. You take from 1 n equals 1 until you're exhausted, or until you've got an answer. I should have included that in the comments here. Until you find a model that can do the job. So roughly 150 models is the number. And there's talk about, last year I presented these images of graveyards and backyards where I buried the models in that. So it was in 2002 that the very first crude toy model that actually works was found. I have to say at that point I was convinced there was no such model, and I was proof that it was impossible. And I had to include all the special cases. Nonlinearity, I did that. Nonlinear oscillator, 3-level systems and 2-level system, and 2 oscillators, and so forth and so forth. And I was about ready to write up the paper explaining what was possible. I said, I didn't include loss. Let me deal with loss. And so I thought, well, it'll just take a day or two to wrap it up, analyze loss. And then it occurred to me loss worked differently, and it actually could lead to a model that could fractionate the quantum. So in 2002, I found the first one that could do it. I was unbelievably excited. I've got it. There's no more mysteries. We can solve cold fusion. So I expected this would solve the problem. And what I found subsequently is that it only solves part of the problem. Namely, it gave me good mechanisms which worked qualitatively exactly like I understood cold fusion to work. I mean, it's gorgeous, beautiful. The only thing is that when I plug in numbers to try to connect the experiment, I was off by orders of magnitude. So the toy model, I think, clarifies basic mechanisms. But the headache is that because it required a strong coupling between vibrational excitation and internal nuclear degrees of freedom. And if I was honest about that coupling, then this model couldn't connect with the experiment because the coupling was too weak. So I think that this was part of the problem, but it wasn't the whole problem. I had part of the solution to the problem, but it didn't have the whole solution. So that leads us to a statement of a new theory problem. So the coupling was too weak. Go back to the textbooks, and the textbooks say no direct coupling between vibrations and internal nuclear degree of freedom. In fact, more than that, the textbooks, in fact, my textbook says this problem separates exactly for the non-relativistic problem. In fact, I teach that to the undergrads and the grads. For the relativistic version of the problem, there's very nearly an exact separation of the problem. And so there's no obvious solutions, but it's clear from this exercise plugging in the numbers that you need a direct coupling that's strong to make the numbers work. So this leads us to a new algorithm And this new algorithm can be stated pretty simply. So there's only two approaches. Start with a non-relativistic problem, analyze it, conclude that the center of mass and relative problems are right exactly, which is in the textbooks. That's my textbooks and what I teach. So we conclude that this approach doesn't work. So then we go to a relativistic version of the problem, we can analyze that. And we can analyze it pretty well. So we can solve this one, we can solve this one. And at this point, we conclude that there's no wrong. We look over experimental data and then repeat this. And I repeated it at least a dozen times over the years. And this time, instead of repeating until the problem's solved, you repeat less than a miracle to arrange mass and internal nuclear degrees of freedom. So that I don't know if this conveys a sense of just how hopeless and how hard a theoretical problem this is. But an infinite number of models that can mix. The idea is that if you randomly train one after another, you know, even if you've got bad luck, if you persist long enough, you might hit one that's the right one. But in this case, you've got only two models that could conceivably be relevant. And this one can be exactly, and it's trivial, and there's no, and it doesn't work. And this one got studied in the literature 50 years ago and it was analyzed and understood, and it was known that it doesn't work. So you have this. So the only thing that's left is to go back and stare at the experiment, because then if you can decide that the experimentalists are incompetent, you can disregard the experiment. Then you've solved the problem, because then you don't have to keep looking back at these two problems. Anyway, algorithm. We need a new experiment. Independent of the theory problem, we need a new experiment. So the issue is we've got another headache. In the Fleischer-Pons experiment, because the helium-4 doesn't have any energy, you don't get to see what's going on microscopically. So a normal nuclear physics accelerator experiment, you blast two objects together, you get all kinds of stuff splattering every which way, you detect everything coming out, and you tell exactly what it is that happened when they hit. In the Fleischer-Pons experiment, there's a curtain up. You don't get to see any of that. And so if you have the right answer, I suppose that the angel of God came down and wrote down the blackboard, this is the right answer, here it is exactly, you can calculate it to the percent level of arbitrary conditions. There's no way to tell whether the answer is right, because for the Fleischer-Pons experiment, you don't get to see anything coming out. You got no diagnostic. So even if you had the right answer, you couldn't tell whether it's correct or not. So what you need is a different kind of experiment. You need a different kind of experiment such that if the vibrations couple to the nuclei, that you can see it happen when it happens. You give some energy to a nucleus, for example, the nucleus gets excited, maybe it decays, and if you can see it, you can watch it decay, then you know that you've excited it, which means you know that you've transferred the energy. So you absolutely need a different kind of experiment to see how this basic physics works. And in my view, that's the only way to sort out what's going on with Fleischer-Pons experiment. You need a different experiment. So I put in a design. So I said, suppose we vibrated a sample and we wanted to excite a nucleus. Which nucleus would we excite? Obviously, the one that has the smallest excitation energy. That turns out to be mercury isotope 201. It has an excited state of 1565 electron volts. So here's the list of candidates. This one's number 1, that's number 2, number 3. I happen to like number 1 better than any of the others. If you're willing to work with unstable nuclei, there's lower energy transitions. One of them's in plutonium, one's in 238. I was thinking, excuse me, can I order a couple of kilograms of, it's for experimentation. What? they'll be at my door soon. Okay, to pick me up. Okay. So I worked on the design of an experiment. And if you excite the level, it will give you an electron. Most of the time, it will give you an X-ray some of the time. And if it gives you a lot of X-rays, they'll be directional if your vibrations are in phase. So this is really cool, but more importantly, important choice. The idea is that if I vibrate this, and if I put mercury in the surface, or have a mercury-containing sample, if it works, I could tell it could work, and I could tell it could work by the mechanism I'm describing, because the X-rays will come out directionally. And the directionality is to the same phased array things in high harmonic generation. So this seemed perfect. This would be a way to tell exactly what's going on. I went through the design exercise. All I needed was a couple of meter square area, very flat. I needed a terahertz vibrational source, which probably had to be the megawatt level or something. And I hook everything up and I drive it and put mercury on the surface, then I should get both the X-rays coming out according to my design. And then it occurred to me, Carbu saw collimated X-rays near 1.5 keV coming out of his experiment. And so here's his experiment, low discharge, cathode, collimated X-rays coming out and imaging them. He's able to image the cathode by an pinhole camera from these collimated X-rays. And here's the spectrum, a little bit of a broadband spectrum around 1.5 kilovolts. So this is Carbu. So so the X-rays that are collimated near 1.5 keV sort of smells like this 201 mercury transition. X-rays nearly independent of the discharge gas, nearly independent of cathode material, and he claims up to 20% conversion for electrical energy into collimated X-rays coming out. So not a small effect, a very big effect. The only thing is whereas my design was meters and megawatts and stuff, Carbu's thing was a centimeter and much lower power. And I thought, so the interpretation is that maybe Carbu's actually implemented what I was trying to design and wanted to make happen. And if so, then I should be able to take theory and my ideas and apply them to Carbu's experiment. And if I do that, I plug in the numbers. Well, I plugged in the numbers and I saw by orders of magnitude. But the big idea is that I could use Carbu's experiment to debug my model. And that was the big issue. And Carbu agreed with the earlier conclusion I come to that I needed a much stronger interaction. And so what this means is I need a direct coupling between the vibrations and the nucleus to account for this, which means I have to go back to my algorithm. So I'm back to my algorithm and check the non-relativistic power again, separated exactly like it's separated for the past few hundred years. I went back to the relativistic problem and I went through this iterations and I stared at experimental data. And I continued this, and it says continue this until a miracle occurs. Then the miracle occurred. In a sense, this was completely unexpected. I didn't see any solution to this. But what happened is that around the first of the year 2012, finally understood that there was some fine print. And the fine print basically sort of says that the center mass degree of freedom and the relative degree of freedom separate almost exactly under most conditions. A tiny bit of fine print that says maybe, just maybe, there's conditions where the separation is not relevant or not important. And that's basically what I found, is that I found that the algebra for this relativistic problem is almost the same as the algebraic structure velocity spin boson problem fractionated quantum. And under those conditions, the relativistic problem acts like it didn't separate. And that's what I found. And that leads to a no fundamental Hamiltonian. Here's the new fundamental Hamiltonian. For those of you who sort of know the physics, you recognize it. This term, this term, this term, this term, this electron kinetic energy, these are all Coulomb potential interactions. All of this is exactly what you'd find in the textbooks. The only thing that's different is this. And what this is saying is that I'm replacing the kinetic energy of the nuclei with its relativistic generalization. And I'll be talking a lot more about it tomorrow. But the argument is that this is the answer. That this allows for description of the direct coupling between vibrations and internal nuclear degrees of freedom. And it does so in a way consistent with nuclear physics in the limit that you separate the relativeness of the, you separate the strong coupling, eliminate this to first order, and get the equivalent non-relativistic problem out of it. It reduces to the textbook case. But this one's sort of the next step forward. It generalizes the problem, and in my view, allows us to perhaps get a systematic description of all of the anomalies. So I'm thinking, have a mechanism. I have a new fundamental Hamiltonian. Looks like a solution to the theory problem. Looks like now we have a way. Eventually, this model, this approach appears to be numerically consistent with Carpet, which means that if I could answer, I'm pretty sure give the answer. Namely, I did some estimates which could have ruled it out. It didn't rule it out. It can give fractionation power that looks to be consistent with what Carpet's experiments do. And at least as far as what I know, probably also for Fleischmann bonds as well. So we have this new fundamental Hamiltonian. We'd like to work towards a direct comparison between the new theory and experiment. To make this work, we need data from controlled experiments. Basically, I need to hammer on this stupid model more, get some more quantitative predictions out of it so we can get some comparison. There's a lot of work. Anyway, here's the takeaway message. Probably you remember back in day one, the statement was Fleischmann bonds was inconsistent with condensed matter physics with nuclear physics. And the condensed matter physics with the nuclear physics was, you would say, well, if you want us to buy the experiment, you're going to have to give us a new theory. And if you like, for the condensed matter part of the problem, here's your new theory, at least at the fundamental level. I mean, a ridiculous amount of work to get to the point to demonstrate that it works in all cases and does what's needed and gives numerically correct values all through. I'm going to guess that if this is really right, that work's going to go on for an awful long time after I'm gone. So for the condensed matter part of the problem, here's the Hamiltonian, here's the approach problem. In a sense, we got to do the same thing. Sadly, I didn't put it on this slide. I'll have it tomorrow, but you need basically the same kinetic replacement for the kinetic energy of the nucleon, and then you need the summation of the nucleon potentials, and then you have a new description from your nuclear physics, which would be compatible with this, which you could calculate your matrix elements and coupling with. I mean, again, it's an approximation. I mean, all of these are derivatives of QED, QCD. Those are the fundamental theories that were referenced to. I'm just using them in a way that's a little bit different than people normally use them. Anyway, takeaway message. Questions? We're hit on issues and details. I just wanted to go through it with an overview today to give you a glimpse of what's coming. Comments? No comments. Okay, well, on to my warnings. It's a dangerous field to be in.
Not to anticipate you are right now, or is there, have there been more developments?
It's an ongoing process. I mean, we've made progress on theories. I'll provide an update tomorrow. We've been trying to make some progress on some experiments, and I'll talk a little bit about that. We've been looking at other experiments that have already been done and providing interpretations and that kind of thing. So it's very big.
You mentioned Julian Schwinger and this small number, something that needed to be solved. That was a while ago. So in the population and the collegial relationship around the world who understood what that small group of people were saying, are there people working on this in ways that are related to the work that you and Shadori? I probably didn't pronounce his name. I co-authored that paper. Chaudhary. Is there a larger group of people who see this?
As far as I know, Irfan and I are the only people on the planet that are interested in this particular physics problem at the moment.
When I was here, I went through 4 semesters of physics years ago, and I began to run out of gas on Hamiltonians. When you do Hamiltonians, do you do angular momentum of electromagnetism as well as the transverse motion?
I've looked at longitudinal transverse electromagnetic quantization problems, of course. Yeah.
You mentioned that the Hamiltonian put up is capable qualitative basis to explain the Fahrenheit experiment, which is an up conversion. And now, could you just repeat or just summarize the relationship between up conversion and down conversion as theoretical? Between the two problems vis-a-vis your theoretical model.
Yeah. It's just not my, when in the literature, when people do problems with different basic quanta, pretty much everybody's description is going to provide for up conversion and down conversion, basically with the same equations, the same formulation, and the same dynamics. Namely, the model that shows up conversion shows down conversion. Basically, all of them work out.
That's what I was asking. Thank you.
Yeah.
So this is not my field. I don't understand about Hamiltonians, but you call it a new fundamental Hamiltonian. Does that mean that there's a catalog somewhere of pre-existing Hamiltonians, and this one had to be developed in order to accomplish the energy conversion?
Your question's a great question. It is basically true that for fundamental, in the old days, in particle problems with forces, then there's a Hamiltonian for relativistic problems with classical interactions. There's a Hamiltonian number of these fundamental Hamiltonians that have been figured out, compared with experiment, and are agreed upon and are known that's right. For the quantum problem, there were It's non-relativistic Hamiltonian sort of for condensed matter problems, kinetic energy and potential energy for electrons and nuclei. In classes these days, it's a fundamental Hamiltonian that's widely used and provides a foundation for a lot of what we do. There are similar relativistic Hamiltonians that are widely used to do relativistic corrections. For quantum field theory, for electrons, positrons, and photons, there's quantum electrodynamics Hamiltonian, which evolved somewhat before 1950. And for that area of physics, that's like the last step forward for these Hamiltonians. You don't need another one for that area of physics. For nuclear physics, quantum chromodynamics came around by 1960. And it describes quarks and gluons. People these days still use that fundamental Hamiltonian to add electroweak and a few other degrees of freedom. They're taking QED, QCD, electroweak, and put them all together to form standard model. Quantum mechanics, fundamental Hamiltonian Lagrangian for all of physics, basically, except for all of sort of standard physics, except for gravitation. These days, a huge number of physics folks are working to try to put together Hamiltonian, if you like, or Lagrangian, or bigger objects, which would have it all work together with gravitation and for force, strong force and weak force, and then have gravity work in the same picture. So that model, that and presumably that would be found some experiments describing additional degrees of freedom in the new Hamiltonian form. So the answer is that there's an exceedingly short list of important, relevant, fundamental Hamiltonians, and there haven't been any new fundamental Hamiltonians added to the list for a while. And in a sense, this isn't, I mean, from my perspective, the field theory Hamiltonians really are fundamental for their disciplines. I don't expect anyone to change or rewrite them in any substantial way anytime soon. And my argument is that I'm cooking up, basically doing my best to try to the fundamental Hamiltonians and derive quantum mechanical description, much simpler than the quantum field theory description, that I can actually use to have something like this down. There's still the issue of getting the matrix elements here and the matrix elements here, which requires the equivalent kind of formulation for the nuclear problem as a way to begin to calculate it, except for there's people out there doing QCD calculations directly, making use of a huge amount of computer time doing quantum Monte Carlo type calculations. So in principle, mainstream science went cold fusion, so there's this barbed wire fence up, so it's never going to happen anytime soon. It could.
I think I answered before, but the question of symmetry is of course, a very famous theme a long way, and the complexity of the thing that you're trying to analyze perhaps has some yet unknown properties that could be helpful in formulating the analysis. So my general question is, have you had time, or have you already come to some understanding of the relationship between symmetries in the problem that you're looking at and the properties of the Hamiltonian you're looking at, or potentially new ones that could reveal some conservation laws at some high level.
Your question's by the bootstraps. We've been trying all along to make as few statements, new statements as possible. And once we've got a statement or theory and mechanism of fundamental Hamiltonian, to work with it to try to see whether we can actually calculate something and get an answer out of it and then compare against experiment. So as a result, I'm afraid that the kinds of things I've been doing with these models are sadly, horribly mundane and trivial. I just trying to get some numbers to see if the model can possibly relate to the experiments I'm interested in. And even at that level, I've got precious few numbers out of it. The notion of looking for symmetries and stuff, in a sense, the problem is a little bit different than what folks have been dealing with before. So for example, if you're dealing with atomic physics or nuclear physics, then you got angular momentum, you got translational symmetries, you got parity, you got spin, you got isospin, you got all this stuff that people have understood and they've known about for ages and ages and ages. So all of that in principle is already included in the working out of the QCD part of the problem that goes into these matrices. The issue that's different is that we're interested in coherent energy exchange under conditions of fractionation. So in general, people haven't been interested in that problem. In fact, probably the majority of the relevant physics community would tell you that it's completely impossible. I've made an error somewhere. So as a result, what would be interesting would be the symmetries that are related to your ability to do coherent energy transfer under conditions of fractionation. And at the moment, you know, I understand some things about that problem, but I don't have really good general symmetry statements or group theory statements associated with that at this point.
Well, the good news is that the mathematicians have, for their own artistic purpose, have generalized the Noether theorems considerably into a very, unfortunately, an arcane formalism that they only themselves can read. But that's the bad news. The good news is that the machinery is there, so that connecting to it with even a Hamiltonian such as you have up there, with perhaps some indefinite structures.
You know, it's really strange. Last night I was thinking I was going to come up and I was going to talk, and somebody was going to ask me about Noether's theorem and this stuff. I thought, no, Peter, you've been silly. Nobody's going to ask about it. I had actually spent some time thinking about it, and I thought, you know, Noether's theorem basically says that if you're invariant under transformation of some sort, then you get to look for a conserved quantity. And out of the box, it wasn't obvious to me that I've got to. Okay, so you're going to say that when I'm analyzing for the coherent energy exchange, that it's actually a transformation in the direction that I'm going, so I should be able to use some version of that machinery. Anyway, it's to be thought about. I don't have results of that.
Well, one of the practitioners of this very modern formal approach is your now emeritus colleague here, Bertrand Constant. He and the Frenchman Swartz formulated this very abstract generalization. So I would be happy to, well, you may already know them now, but he's immune to the antipathy you would describe. He has no issue to worry about. He's already Well, it's legacy.
Let me answer quite simply. Your thoughts are extremely interesting. Your suggestions are useful and valuable suggestion. Sadly, I foresee my time being taken up certainly in the next few months, if not most of this year, plodding away on sort of the simple kinds of things. But I am aware of the issues and I am interested. So what I'm going to do is, what I'll promise you is I will muse about it. At the time when I can pull my head up out of this particular hole that I'm digging, then I'll return to the question.
Well, I have a different reason for calling him Cossack myself, so I'll mention your name. He might call you.
All right, very good. We've gone over it a bit. I think it's time to say thank you for interesting discussion today and revisit things tomorrow. Thank you.
Yeah, I don't know if Sharon just up there's an interesting moment there when you're standing in front of slide. The little problem with slide is always right on. I mean, sometimes your forehead is right on. Your name was right across your forehead.
So this is
Are we off?
Yeah, we're closing up now. Hey, this is the end of the live stream. A couple people on here were saying they had some problems with the audio and everything. I'm doing my best to try and fix that. And if anyone else out there has any suggestions on how I might be able to live stream this a little bit better, then please let me know. I'm all ears. This is the main problem I have. I looked on a bunch of forums to find a solution to it. They keep auto-adjusting. Google Hangouts keeps auto-adjusting my microphone gain on its own, so it keeps going up way off the charts and it keeps going up to 100. So I have to literally sit here for the past 5 hours, 4 hours, whatever, and fight with this volume control knob. I found a fix for that. I'm going to try that tomorrow, so I don't have to do that. I have to go and do some registry edits and stuff. But if anyone else has any ideas on how I can improve the quality, the video, some people are saying that they're not getting 720. I'm here connected to the MIT internet right here as a guest. I don't know if there's any other way that I can get faster internet connection, but if anyone has any ideas, please feel free to email me and let me know, and or just leave a comment in the video here and just send me some ideas. So I'm trying my best, and this is again a new technique. So let me know what you guys think or how it works. And that's it for the day. Thanks for watching.
This is the control.